All right, hi there. Okay, for people joining us, we are doing an unusual Saturday live stream. Actually, we might do many more of these. We're so excited about the progress we're making in Metamathematics that we think we have to go on today. So what we're talking about is in our model for physics, we have sort of a framework for thinking about how systems work. And the question is, to what extent is that framework shared with a framework for doing metamathematics? What we have been discussing last time was particularly, we have known forever that our multi-way systems can also be thought of as systems that correspond to kind of processes of mathematical proof. So I think the analogy is something like this. In the universe, time progresses and computations happen and new states of the universe are computed. In mathematics, the analog of time is the progress of mathematics, so to speak. You have a certain set of theorems that have been established, and as mathematical progress progresses, so to speak, from those theorems, other theorems follow. Just like in the history of the universe, we have a certain state of the universe, and from that state of the universe, as physical time progresses, new states of the universe are created. And so one of the things that we were talking about last time is we were talking about all kinds of things. And actually, Jonathan, I hope we didn't lose the notebook that we created during the live stream last time.
No, I just sent it to Jess.
Oh, okay, terrific. Because we didn't even tweet about it. We were so intense here that we forgot everything. But anyway, well, let's see. Well, should we summarize? I mean, at least from my point of view, some of the interesting things that came out last time. When we think about I was literally just working with one of our summer camp students on a thing which is actually surprisingly relevant to this. We were looking at, his project had been to look for multi-way systems of intermediate growth. And so we were just looking at, let me just pull this up in the right form. We were just looking at this multi-way system, okay? And the question really is, here, let me just create this one somewhere else. And I want to sort of give an analogy with mathematics, and I want to understand the analogy here, and then I'm going to turn this over to Jonathan and Xerxes. I just want to take this as an example. Okay, so let's just understand sort of the analogy. So this is J-random multi-way system. And I think the interpretation that we'd had before is to say that these strings could be the analog of mathematical statements, basically. Things like A dot B is equal to B dot A. And then these arrows, in this case, would be things which follow from one mathematical statement, you deduce another mathematical statement. And the notion was that unlike just saying this is equal to this, what we're saying is this statement, which might be of the form A equals B or there exists or whatever, this kind of network represents the derivation of new mathematical truths from old ones. Are we on board so far, guys? Yes? Okay, so now, one of the ideas, which I think was a Jonathan idea last time, was the notion of something follows from something else. It is true that something follows from something else if you can follow an arrow to go from one thing to the other thing. It is false that something follows from something. You can tell that it's false if you would have to follow the arrow in the opposite direction to go from, let's say, from X to Y, that X implies Y is true, but Y implies X. That, in other words, that there's we can attribute, we can say, what is a correct mathematical, what is a true mathematical inference and what is a false mathematical inference by asking, what follows the partial order of the multi-way system and what definitively isn't correct because it goes the opposite way in the partial order. So now, question here is, well, that's one statement. So another important observation of last time was the idea of the relationship of model theory. So, you know, proofs correspond to paths in this graph, right? And one thing that is not usually considered, except in homotopy type theory, is the idea of multiple proofs that go from one statement to another statement. But one of the things that we discussed a lot last time is model theory, and the question of when these, of what it means to make models. And I think what does it mean to make a model in general? So you have some, like for instance, you might say, we've got some axioms, you know, f times, I don't know, you know, f of a, b, you know, equals, well, let's say here's a typical case. So this would be a, that's an axiom, and then we could add some other axioms, and then this would be, the models of this would be, let's say this might be, if I get this right, this might be kind of a abelian semigroups or something. Maybe I need an identity element as well. But so the models would be, what multiplication tables for f and what values for a and b can I use so that these turn into things which I can readily compare. And so I think one of the observations of last time was we can think about, when we think about foliating this multi-way system, we are thinking about kind of we're coordinatizing this, and coordination is like putting models down on this. And so one question here is, like, we're trying to prove that this particular thing has, I don't know, exponential growth or something, right? Now, one way to do that would be to say, we have a model, and the model is such that we know, and if we look at the length of the string, that the length of the string will be uniformly increasing. In other words, given the model, we can immediately deduce things about the behavior of the system. The model gives us a way to kind of have a, you know, to make deductions about how the system will behave that is different from the kind of purely symbolic, syntactic sort of set of deductions that we can do within the multi-way system. Well, then I think the interesting analogies are things like, you know, we've got these models, and these are kind of like reference frames of some kind. But there are pieces to this analogy which need further development, and they're interesting kind of. But anyway, maybe I should turn this over to Jonathan or Xerxes for a while, and we could either talk about this, or you can launch into the continuation of what you were discussing before. Do you want to talk about this for a minute and respond to that kind of the models question and so on?
Yeah, sure. So we can, although as you say, there are some other things we didn't even get a chance to get to last time, like you know, Xerxes' realization of the relationship between what we've been doing and sort of monoidal category theory and categorical quantum mechanics, which I've just yesterday, I think I figured out something new about, which I'd quite like to sort of explore, because I don't know exactly how it's going to work out. But okay, let's start with the model theory stuff. So I think, okay, last time we were discussing the analog of non-constructive proofs in these kinds of systems, right?
Indeed.
And we reached this conclusion that a non-constructive proof probably corresponds to a light-like path, right? And so this, okay, so I think there's a general point to be made here, right? Which is that things like Rulio multi-way systems are both a good model for mathematics, and they're a good model for computability theory. And you know, originally we were thinking about them in terms of computability theory. Now we're thinking about them in terms of mathematics, in terms of metamathematics, and in particular in terms of proof theory. And given that correspondence, it therefore seems natural that the interpretation of model theory, you know, with respect to proof theory, is very much like the interpretation of computational complexity theory with respect to computability theory, right? We're now comfortable with this idea that the Rulio multi-way system defines a topology on computation, which is computability. And then when we coordinatize, when we define a gauge, then, you know, it's like we're defining an explicit model of computation, and we can then start computing geodesic paths and things like path lengths and things.
Right.
So effectively, these questions about what are the maximum speed of proof and so on become questions about what can you actually achieve given bounded computational resources. And so the point is that when you define a model, you as a mathematician always have bounded computational resources. And one implication of that is that you're always constrained to live inside your proof cone, right? You can't, because effectively to witness explicitly a proof that lay on the boundary of the proof cone would require you having unbounded computational resources, right?
Well, no, I mean, on the boundary of the proof cone, you're going to be going down this thing this is starting from any proposition here. The proof cone is defined by it's the boundary of what you can reach from that point.
Yes, yeah. But
I mean,
I know what a proof cone is. So.
Yeah, right. But I mean, I think the issue is, what does it mean to make models here? Models are a way of, we have a bunch of mathematical axioms. The question is, are they about anything? Are they just abstract syntactic axioms? Or are they about something? Are they about integers? Are they about particular semigroup? Those kinds of things, right? And so...
But the point is defining that domain. Okay, so defining a model is equivalent to defining a domain of discourse. But defining that domain of discourse is itself a computational procedure.
I agree.
Right? So because you have to find a set of elements that are consistent with the axioms, over which to quantify.
Yep,
so the point is being able to follow all possible proof paths requires you in effect to be able to do an unbounded amount of computation in setting up the model. So if you have bounded computational resources, you are constrained so that your model effectively has a finite mass, so to speak, corresponding to the fact that your computational resources are bounded. And so the set of proofs that you can actually explicitly witness are the ones that lie within the interior of your proof cones.
I agree. But let's say it out a different way. You've got what a kind of model-like hypersurface is, so to speak. You are, and I don't completely understand this, and I want to take this as an example here, and I want to understand also a little bit more detail how the automated theorem prover represents, a multi-way graph, a single path here with little stubs in it and so on. I don't completely, there's some pieces of this I don't fully understand, which I'm hoping you do understand.
Yes, yeah, but, I've just been writing about that.
Okay. So anyway, so we've got in here, do you understand? Okay, so if I think about, for example, let's say that one aspect of modeling is to just look at the lengths of these strings. Okay? So in other words, when I make a model, what does it mean? I'm going to take one of these strings and I'm going to have a representation of it which can be thought of as coordinates of some kind. I mean, that's a way to think about, so a model, for example, in here would be to say, I'm going to have a particular multiplication table. I'm going to take particular values for A, B, and C, and so on, right? Mm-hmm. And then I will have, so my question is, if I foliate this multi-way system, I'm going to have a bunch of layers a bunch of layers where I say that these things are somehow, they correspond to a particular moment in time, so to speak. Help me understand how do I think about that? I mean, in other words, I'm thinking about, let's say that the length of the string was a coordinate that I was going to use here, which was one thing that was sort of related to the way I construct a model for these things. And then I might be able to say, oh, it's really obvious, the length of the string always increases here. So just from knowing about the model, I can say things about what will happen at future times.
Yeah.
There's something to untangle here. Explain, when we think about a model, how would you, okay. What you're doing is you're saying,
well, look,
go ahead.
So the point is that the partial order induced on the multi-way system, as we discussed last time, tells you which terms are equivalent syntactically. Mm-hmm. In addition to syntactical equivalence, you can also have semantic equivalence. You can have particular values of A and B for which f of AB equals f of BA, even though that isn't true syntactically.
Exactly.
right? So the model, the foliation, is defining additional equivalences between terms that would not have been equivalent under the original partial order. That's all that's happening.
Let's be careful about what we mean by equivalence here, okay? So in this setup, we're saying that this follows from this follows from this. We're saying this chain of following can be affected by, we can have additional chains of following that are a consequence of the foliation that would not be there just as a consequence of the structure of the multi-way system.
Yes, exactly. Right. I mean, I can show some pictures if you like.
Yes, that would be good. Yeah. Okay, maybe go ahead. Why don't you show your pictures that way? Hold on, let me unshare here.
Sure. Okay, so, all right. Okay, so if you consider, let's take a kind of useless foliation, a kind of essentially an empty model. So this is a model that is just, the only equivalences are the syntactic equivalences, right? So this is a model that has added no new semantic truth other than what was already syntactically derivable. Does that make sense?
Let me ponder that question for a second. So your claim is that
there is no new order structure that was not already present.
Yeah, I know. It just takes me a moment to be convinced that that's really true. Yes, I believe you. Okay.
Okay. Here's a non-trivial model, right? So one in which there are now new, because this model is consistent with the partial order, the reference frame is consistent with the partial order, everything that was syntactically provable is still semantically true, but there are new things that are semantically true that were not originally syntactically provable, like, for instance, AABB goes to ABBA.
Right.
Right. So all that's happening is you can think of a model as defining an additional set of equations that did not exist purely on the basis of syntax. So those would be cases, like I say, where you get, where f of AB equals f of BA just by some numerical coincidence as opposed to some theorem of algebra.
Well, or you've got a particular group for which something is true.
Yes, like commutativity, right? So
yeah, right.
In all groups, the identity element commutes with everything, even if the group is non-abelian.
Right.
So that's what I mean. So f of AB equals f of BA because of a numerical coincidence rather than a theorem of algebra.
Yep.
Okay. And then yeah. So this would be the corresponding.
Well, actually, I don't like your numerical coincidence claim. Okay. I mean, it's really a matter of a model. It's a matter of this thing now being about something, right? It's like you've got abstract group theory, and then you've got the theory of a specific group, the icosahedral group or whatever. The icosahedral group satisfies the axioms of abstract group theory, but it is...
And has additional equivalences.
Right.
That's all that I'm saying. So I don't...
Yeah, okay, fine. Fine. But your numerical coincidences makes it sound like it makes it sound like an add-on, whereas I think for many people, this is the essence of what, when mathematics talks about things, it does it this way. Keep going.
But it is an add-on from the point of view of metamathematics, right? That's what distinguishes group theory from universal algebra.
Yes.
Universal algebra is about what's true of generic groups. Group theory is about what's true of specific groups. So it's definitely an add-on. Group theory is universal algebra equipped with some additional set of equivalences that you can represent as a
which are the group relations for a particular group.
Right. And so the other thing, which I think I've managed to make a little bit more precise since our last discussion, was this notion so you can have models where effectively the models are free in the sense that the only equations that they define are the equations that are already consistent with the axioms, and those are like inertial frames. But you can also
that was what the original frame that you showed there, you claim, is like that.
Right. But even these are you're not.
Well, it's a good point. I mean, what you say is that like a free group is one that has no relations. And whenever you are adding relations, you are specializing to something beyond the free group. You've got various other kinds of equivalences.
Right. So this is still a relatively free object, but obviously the more generic case is something like this, which is where it's definitively non-free, right? The model is defining all kinds of new equivalences that are not explicitly implied by by the original syntactical
So
structure.
can you write down, given a foliation, can you write down, I don't think we've really thought about it that way, can you write down the implied equivalences? Is there an easy way to do that? And is there a way to think about that in terms of, I mean, in other words, given a completion, for example, does it imply a foliation?
What do you mean?
Okay, so a completion gives you additional...
You mean as interpreted as an equivalence, then yes. But the completion is a procedure, not an... I mean, the critical pair lemma is the equivalence.
Fine. Yes. Okay, so you add a lemma. Given one of these things, one of these sort of trivial crisscross, evolutions, if you add a lemma, what does that imply? You're saying then that you go from the free foliation, adding a lemma. In what sense does adding a lemma go from the free foliation to another foliation?
Well, so suppose we took, okay, let's start from this case, right? So suppose we took this element and this element, and we defined an equivalence between them.
Yep.
Right. We can do that because they're not, their relative order is not specified by the partial order. So if we add a critical pair lemma, we can consider these to be both elements of a critical pair starting from, say, this element. So we can do that. And when we do that, we are defining a local slope, right, between this point and this point in some coordinate system.
Yes. So what does that look like?
So if we extrapolated that equivalence out, we'd get we'd get an inertial frame. But if we say let's specialize that equivalence so it only holds for these two objects, then what you'd get is a curved frame where you had something going up here, going to this point, going up to that point, and then going flat again.
Walk me through that more carefully. I don't quite understand that. So let's take a look at this.
This is an explicit example, right? So AB, ABB, and ABB, AB are not syntactically equivalent, but they are now model theoretically equivalent.
I'm confused here.
This is what you would induce if you applied a critical.
No,
pair.
I'm confused by what would the equivalence, the statement of equivalence, right? Because is within that slice of the foliation, you are conflating those things by this new lemma, basically. But yet, what we're talking about in terms of equivalence is we're saying that the theorems we're proving are the equivalence of things syntactically going down the page.
Right.
Okay, so something is confusing to me here.
Why?
Well, because on the one hand, we're saying the arrows down that lead downwards in time, so to speak, correspond to the time-like edges correspond to the true inferences of mathematics, so to speak.
The syntactically provable inferences of mathematics.
Right. Okay. But now, what I had understood was that if we take a model here, we're now identifying different kinds of things as so in that model where it's going off to the side, right?
Yeah.
We're saying that there are things which, as we walk down. Oh, I'm confused here.
There's a total order induced, and the things that are consistent with the total order are either syntactically or semantically true. Okay,
but take an example of something which is in the total order, but not.
That's what I just did, right? So let's do an example of that. So if we do states graph structure, we could do, so AB, ABBB, and ABBA are not connected in the partial order, right?
That is correct.
So we could do highlight graph ABBA and what was it called? ABBB. Right. Okay, so then let's define a critical pair lemma that connects the two. So when we do that, what we're inducing, if we imagine that equivalence is extrapolated out, what we are inducing is this foliation choice where now this one does precede this one in the total order. I mean, that's what a total order means.
I managed to get myself confused here. Let me just understand. I may have to go back and look at what I wrote about these things before. So let's see. Normally, in the notion of total order here, what we're saying is successive slices of the foliation correspond to successive, quotes, moments in time, successive elements in the total order, right?
Yeah, there's a universal time function which defines simultaneity between points.
Right, but then those two things there are in the same time slice.
No, they're not. This one's on, or maybe this is a bad example, right? I was trying to plot it so that, well, hang on, we could do, let me fix it up a little bit to make it a bit clearer what I'm trying to say, right?
That's a total hack, yes.
That's the point
okay.
I was trying to
make. All right, okay, now I understand. Okay, so you're saying, okay, I was very confused by that, right? So you're saying that those correspond to, I mean, it would have been perhaps clearer to me if those had been in different slices rather than on the slice boundary, so to speak, but it doesn't matter. Okay, yes, I understand. So those two things then become on different, what we might call semantic slices, and therefore one follows from the other in that ordering. And what you're saying is that ordering is being added by adding additional relations over and above the free situation.
Yes, but this is still a free object, right? Because this is a free model. So this is not something that one conventionally thinks about as a model as a universal algebraic structure. But I think I now have a clean way of thinking about this, right? So this is the free model generated by one equivalence. So we take this pair of points, we add an equivalence between them, and we generate this free model.
Well, you're just saying you've got a group, and instead of taking, however many relations the icosahedral group has, I'm just going to pick one of those relations. Like, a sense of your model would be all abelian groups, for instance, right? Rather than a particular group. I mean, what you say, what you're referring to as a free model is a model which has some additional relations, but
it's
not
a model
enough.
That's generated by a single equivalence,
like the commutativity axiom, right?
Right.
So I mean, that's one of the issues with, in sort of metamathematics, is this question of, the question is this axiom system about something definite? And one way it can be about something is if there's only one model that is consistent with that axiom system. Like, for example, the attempt to make, Peano arithmetic be about the integers are the set of relations defined by Peano arithmetic sufficiently kind of defining that you get the integers and nothing but the integers, right? And we know from Gödel that isn't the case. Although it'd be worth seeing,
because there exist anti-chains.
Well, okay, but so let's just understand.
Irreducible anti-chains, right? That's what the first incompleteness theorem says.
Right, and that's what I mean. But what you're saying is, okay, let's just walk through that a second, okay? So what would it mean if it was completely determined, if there was nothing free anymore? What it would mean is there would be no anti-chains, as you put it. There would be nothing in the slices. There'd be only one thing in every slice. Is that a true statement? Right. Okay, so what does that look like? That
it looks like a total order. I mean,
no, I understand. In which you can basically walk down this graph, and it's like a breadth first search or something, or a depth first search. You go from node to node to node to node to node.
How does path graph work? Can you not?
We give it a sequence. That will be that. What are you trying to do? It'll go from what? Sorry, you've got an I. You say range of 10. Path graph range of 10.
Oh, that's what I was trying to do. Sorry. Yep.
Yeah. Okay.
Oh.
Whatever. Yeah, I know what you mean.
Yes.
Okay, yes, that is a total order. I've seen them before.
Right.
Right. On this multi-way system, I had some nice pictures actually in my technical introduction thing. On this multi-way graph, I mean, okay, just to slightly unconfuse this, okay? A foliation, so the total order walks down from node to node to node to node to node in that picture, right?
Yeah.
Right, but that is to make a foliation which constrains one to do that. It's a very squiggly foliation.
Right.
Right? Now, my question is, what you're claiming is that a foliation is like the addition of relations, basically, lemmas in the mathematics. Whereas being about a definite thing is the formation of a total order, which would correspond to a crazy collection of sort of foliatory constraints. And so let's walk through, again, the interpretation of Gödel's theorem in this context.
Well, the statement that there exist multiple total orders that are consistent with the partial order.
Yes.
So
that's a statement that there are multiple models of pure arithmetic, for example.
Right, that imply different semantic truth values for certain propositions. What part is confused?
No, I think that's perfectly clear. I'm just clarifying it. I'm just making sure. Okay, so now the next claim is about the non-constructive mathematics claim,
right?
Which is a claim about. Go ahead. I mean, okay.
Right,
I'm just. Okay, go ahead.
So if we take an example, let me do. Well, actually, I might as well use the same. Let's do the same multi-way system. Right. So if a model is produced by a computationally bounded observer, then it is constrained to always lie. It is constrained to move subluminally, so in the sense that it cannot move at the maximum speed of proof. Right. That's what it means to be computationally bounded.
I think that's correct, but I just want to walk through that again for a second. Okay.
Okay.
So, I mean, what you're saying is that to create a foliation that would not have that property is something that progressively requires unboundedly large amounts of computation. That is, at one step, you can create that foliation, but to keep that foliation consistent requires things to get squigglier and squigglier. That's your claim.
Right. So if we did something like, so to get a sense of what the boundaries actually look like, I'm definitely going to miscount the number of B's here. There we go. So then if we did this, there we go. Right. So those are paths that are inaccessible to an observer using only constructive mathematics, highlighted out of the space of all possible mathematical truths for that, that are derivable from the given proposition.
All right, let's walk through this. It's a very interesting claim, but let's just walk through this carefully. Okay. So the claim is let's define what a mathematical observer is. Okay. A mathematical observer is somebody who is exploring parts of mathematical proof space and trying to make a model for what's going on, right? As in, what does it mean that they're trying to make a model for what's going on? They're trying to say, these mathematical statements are actually about something. Does that make sense?
Yeah. Yeah, they're trying to define a model.
Right. And you're saying that first point is there isn't a unique model. Okay.
Yeah, but the second point I'm making is also a very simple one, which is that, okay, if we take this default foliation, it is trivial to see whether this foliation is consistent with the partial order or not, because in this case, it's it's the foliation that is the partial order. As the foliations get more and more steep, the task of computing that becomes a more and more difficult computational problem.
Task computing what?
Consistency with the partial order.
Because you have to follow because in exploring parts of the foliation, you have to follow more steps in the multi-way graph. Is that your claim?
Yes, right. Because there's time dilation, right? This comes back to the conjecture I made last time that there should be a model theoretic slowdown theorem. Right. Oops.
Okay, well, hold on. Let's just. I know you are very keen to go on to higher things, and we'll get there in just a moment. I just want to make sure we understand this part. Okay, so you're saying that
so you define a very simple algorithmic problem, right? I give you a model and you want to determine, is that model actually consistent with this particular set of sentences, this particular mathematical theory? In other words, is this induced total order consistent with the partial order that's induced by this, by the set of syntactically provable statements?
Yep.
Right? And so the point is, as the more non-trivial equivalences the model introduces, the more complicated that it becomes to make that determination. And so in particular, sort of the further away the statements are in proof space that you are defining to be equivalent with respect to the model is, the greater that distance is, the more complex that algorithmic problem.
Let's talk about this further away in proof space. So we've got a definition because we know a speed of proof. Because we have that defines a certain sense of distance in proof space.
Right.
What is the interpretation of the speed of proof? So in mathematics, what is our everyday interpretation of the speed of proof in mathematics?
Well, like I say, I think the way to think about it is in terms of constructivism, right? It's in terms of you're measuring the computational complexity of constructing, the objects about which you're reasoning abstractly.
But I think the construction is the creation of a model. I mean, that's the constructivism.
Yeah, right.
But I'm asking, just in our everyday situation, we've got a mathematical proposition, and we want to establish all other true statements that follow from that mathematical proposition. I mean, in a sense, what this is doing is, it's like
that's what I'm talking about.
Yeah.
I mean, that's what this is, right? We have a proposition. We're determining what propositions are determinable from that proposition.
I know. And the
point is that the more steep the time-like or light, the more steep the internal time-like path is, the more complex the problem of constructing for that given proof, constructing an appropriate model that witnesses that proof.
I understand that. I'm asking, in practice, let's say that the thing that you're representing is number theory, for example, right?
Yeah.
Then you're saying to prove all the true statements of number theory in a very Hilbert-like way, right? Your cone there is proving all the true statements of number theory, right? Given all the statements of number theory which are provable in less than such and such a number of steps, right? So.
And the point is that in proof theory, everything goes at the speed of light. So we don't care, right? It only, just like if you're a photon, you don't care about what the speed of light is, because you don't have a notion of time, right?
Yeah, I understand. In proof theory,
the point is you only become aware of the maximal speed of proof once you try to define a gauge or a model.
I still just want to walk through that more slowly. Okay, so it sounds. Okay, so you're saying when you try to define a model, because in defining a model consistently, you're kind of having to deal with not just one path of proof, but all paths of proof, because that's the only way you know that you have a consistent model. Right. It's not enough just to look at one path. Right. If you were the photon, you could just be going down one path in this kind of syntactic proof.
there is only one path kind of for the photon, right?
Right. But what we're saying is to establish that you have a consistent view of the world based on models, you at every step have to gulp in the whole space, so to speak. Right? In order to establish that your model is correct and consistent, you have to be able to look at the whole of each slice, not just the one path that you're looking at.
Right.
And so the statement that constructivism is hard is basically the statement that if all you want to do is make these symbolic proofs, you just have to follow one path. If you want to also know what you're talking about, so to speak, you have to be able to establish that what you're talking about is consistent with all proof paths.
Right, and as I say, just by elementary geometry, the more steep the foliation, the more non-trivial equivalences you have to verify across that. You know, the more objects you have to check are consistent with the partial order along that slice.
Okay, the boost, the concept of a boost in mathematics. What is it in everyday mathematics? This boost idea. I think what it is it's adding more relations. It's making the thing less free, right? That's your claim. Is that boosting?
You're not adding more relations, like I say. So the reason I think this concept of a free model is useful is the free model, as I say, in my formalism for it, the free model is generated by a single equivalence. It's just that equivalence can be arbitrarily weird, right? Because the separation between this point and the corresponding point can be arbitrarily large.
Yeah.
So when you do that, you're defining an increasingly weird model. It's not that you're adding more relation. Adding more relations is making
okay. Fair enough.
Free.
So you're saying,
getting towards
okay. So you're saying the definition of a squiggly foliation, of a boosted foliation, and sort of is one that. So in space-time, the analogous thing would be to say that a fast-moving frame is one that identifies as being simultaneous in time two things that in the rest frame would be very different at very different times.
Yes.
Right. So here,
or they have a lot. There's a large invariant space-time distance between them, and that's all I'm saying here, right? That you're defining an equivalence between 2 points that have a large invariant proof time distance. Right.
Right. So, okay, so let's just understand that the way that generalizes. And okay, so you're saying
because if they're the further away they are in proof space, the more sophisticated the computation is that you have to do in order to determine that they are in fact independent of each other, and that therefore you can define an equivalence that way.
Right. But so in other words, a boosted frame is one where you are defining a model. I'm just trying to relate it to sort of everyday mathematics, where you're defining a model in which your model is kind of jumping ahead in the computation. That is, by saying the model is in one fell swoop saying these two things are equivalent. I'm just telling you.
If you want to use the number theory example, it's the analog of like, you know, you make a number theory conjecture and I disprove it by discovering some trillion-digit long counterexample or something, right? That trillion-digit long counterexample corresponds to an arbitrarily boosted foliation.
I'm not sure I understand. So another way to think about it is
because in order for you to witness that is a valid counterexample to your proposition, you have to do an arbitrary amount of computational work. And the same is true here, right? In order for you to witness that this is a valid model, as the 2 points get further away in proof space, you have to do an arbitrary amount of computational work because you're having to do partial order checks for an arbitrary number of statements in the multiverse.
No, I agree. But another way to put it is this: in the construction of the model, you know, the model is kind of trying to give you a free ride on computation, right? In other words, if you have a highly boosted model, what you're saying is that, oh, you don't need to follow all those steps through the partial order. The model just immediately tells you these two things are equivalent or whatever.
Right, but the trade-off is that validating the model, all of the computational burden is shifted into the validation of the model and away from the validation of the theorems.
Right. Well, or to say, right, so you can either
take templating or something in software engineering.
Right, you can either take the cost up front in the construction of the model, or you can take the cost in the individual construction of the theorem. So this is intuitively like saying, once we have a valid model, once we know that pure arithmetic is about integers, we can just say 2 + 2 is 4. If we're forced to show that from axioms, we do a Whitehead-Russell thing and we spend 200 pages showing that 2 + 2 is equal to 4.
Right. This explains why abstract mathematics is harder than concrete mathematics at some level, right? Because concrete mathematics is based on models that have been pre-compiled and pre-verified.
Right. And pre-done, they've pre-jumped ahead. So
Right.
The question then is, so this notion of boosting in models is a notion of kind of how much work. Okay, so the boost of a model is how much work had to be done in abstract mathematics to establish the things that become equivalent that become in the same slice of the model, right?
Yep.
So how much work, so that's the notion of a boost. Can we just review that one more time? Because I think that this is going to be, because then I want to understand what the actual analog of Lorentz transformations and time dilation and so on are.
Well, that's the model theoretic slowdown theorem.
Okay, which you just invented 2 days ago. So let's understand what that is.
Right.
Just, you make it sound like it's been there for centuries.
Well, 2 days in this project is a long time.
In some boosted frame of whatever. Okay, so in any case, okay, so hold on a second. So okay, this is an important point which I hadn't really internalized. The notion of a boost is something much more general than what I had understood before. That is, the notion of a boost is saying that you are picking a foliation in which the equivalences correspond to things which are going far down in the partial order.
Right, you're defining weirder equivalences, progressively weirder equivalences.
Right. Okay. So now remind us what Jonathan's slowdown theorem concept is. So you're saying, go ahead.
So it's a converse of a speedup theorem, right? So a speedup theorem says that given a certain axiomatic system, there can exist arbitrarily long proofs, but you can kind of shorten those proofs by switching to a more convenient axiomatic system. That's the Gödel slowdown theorem. But sorry, the Gödel speedup theorem. But what we're saying now is that if you pick some model, it takes a certain amount of computational effort to verify a theorem to verify a proposition from first principles. Shifting to a boosted model, it will take an even greater amount of computational effort to verify that proposition from first principles, even though post-verification, it takes less time.
Hold on. So normally, there are 2 steps. Step 1 is verify the model, prove that it's a correct model. That could take a huge amount of computational effort because you've got to gulp down, these big slices of multi-way system and so on, right? Once you've verified the model, and the verification of the model, as the model involves larger, proof length, proof separation, so to speak, proof invariant intervals, gets more and more difficult. But now, what are you saying after that?
Yeah. So the point is, you want your Minkowski norm to equal, to be invariant, right? So this model theoretic slowdown theorem is exactly stating that any gains you make in shortening the verification time for proofs are offset by additional time in verifying the model and vice versa.
Let's just walk through that one more time, okay? So the claim would be.
Okay, should I write it down?
What's that?
I can write it down.
Okay. Yes.
So we could say like positive eigenvalue associated. So Minkowski metric. We have a positive eigenvalue associated with model verification time. Negative eigenvalue associated with proposition verification time.
Okay, so model verification time is like space here.
Right. So then Lorentz symmetry is just the statement that this proof theoretic Minkowski metric is invariant, i.e. any any gains in computational efficiency of proof verification are offset by losses.
Yeah. All right, let's just understand this analogy of model verification time with space. Okay, so what you're saying there is that the slices, go ahead.
Because so like I've been saying, so verifying the consistency of the model, verifying that the model is compatible with the partial order of the multi-way system involves looking at all of the states that lie on a particular slice and checking that none of them are proof-like connected, if you see, time-like connected in the proof space, right? So the steeper the foliation, just by basic geometry, the more such states you're having to do that verification for. So your computational complexity increases, but you've got the analog of length contraction coming from the fact that there are more states lying on that particular slice, more states that you're having to verify. Verify compatibility with the partial order for. Why
is that length contraction? Wait a minute. So because what you're thinking about is the semantic, the model-based. I'm somehow reminded of the whole model-based design engineering discipline, but let's not. It's a different kind of model. Let's not get confused. Okay, so the model-based mathematics basically involves going down through this foliation and stepping through the foliation. That's our observer that's traveling at a certain speed. That's our observer who's already determined that they are going to view space-time, so to speak, or whatever it is, proof time or something, in that they're going to view it relative to these equivalences that they've defined, and they're. By the way, what is the precise analog? So time is the progression of proving things. What is space? What is the analog? When we say space-like hypersurface, what is the correct term for that here? So the model is the set of equivalences that have been defined.
Yeah.
And that is that's like saying that is simultaneity. Model equivalences are like simultaneity, right?
So sorry, I missed the last part of that. What?
I said model equivalences are like simultaneity.
Yeah, right. Oh, well, I mean, simultaneity is just a different time-ordered equivalence relation, but
No, but you should write this down because I mean, basically, when you define an equivalence, right, from a model, that is like defining a simultaneity surface in relativity.
Yeah, that's what I'm saying. Just like defining an observational equivalence surface in the multi-way system is like defining a simultaneity surface in relativity. They are all just time-ordered. All of these are just level sets of some universal time function.
I'm just trying to get straight the language of if these equivalences, right? Simultaneity. Could you just write down for my benefit, just so we know?
Simultaneity is an equivalence relation. They're all the same, right? We're not.
I know simultaneity is, okay. But okay, that is.
I can write simultaneity is an equivalence relation.
I know that, right? But is an example, right? Simultaneity. But when we talk about space and time, I'm trying to. What is the analog of? What is the correct word for a space-like hypersurface in this model, in this setup? What is the correct term for that?
They're a set of independent propositions, right?
Okay, so you're saying, so let's be very careful. Let's try and make a clear word for what that is. Okay, space-like hypersurfaces are hypersurfaces simultaneous in time that exist in different places in space. Okay, so are propositions that are considered mutually independent.
Well, they are mutually independent with respect to the model.
Yeah, okay, they are mutually independent. But now, okay, fine. But now, when we talk about space, when we talk about moving in space, right? What is the analog of moving in space here? It's moving between these independent propositions.
Right.
So what is that? I mean, is it like when we talk about space-like separated, what are we talking about here? Right, right. Spatial motion defines equivalences. Well, spatial motion corresponds to a foliation which is set up by defining equivalences.
Right.
But I still want to come back to what is the right name for moving in this space-like direction? Those are things which are not connected by proof. They're not connected by syntactic proof. The heck is that?
Well, you're defining new sets of equivalences between mutually independent propositions.
When you have motion, but when you're just...
Yeah. Isn't that what you were asking? What's the analog of spatial motion?
Okay, just tell me, in the sentence, there are space-like hypersurfaces orthogonal to the time-like direction. What is that sentence in this case?
There are sets of mutually independent propositions with respect to the model. Orthogonality to the time-like direction is the statement of mutual independence, of the, i.e. consistency with the partial order. It is consistent to view them as being...
Okay, so is this something we have ever thought about in mathematics before?
Not to my knowledge, no.
Let's just explore that for a second, because it's always interesting, given that mathematics is an old business, and we happen to, on this random Saturday afternoon, be thinking about something that seems like a fairly fundamental feature of mathematics that we think hasn't been thought about before. It might be worth us spending just a moment to ponder that question, right? So these mutually independent sets of propositions that are not connected, which cannot be proved from each other, these are kind of, they're sort of like the scattered facts of mathematics, right, that don't... Where have we seen this before? It's like these are... Where has one seen that before? Well, I don't know. All right. Okay, so you just go ahead.
There'd be things like the axiom of choice, or the continuum hypothesis, or Whitney's theorem, or whatever, where it's like, we have gauge freedom to determine whether or not we want those to be true or false.
So you claim, I mean, like large cardinals or something, you claim that this is in the higher mathematics, so to speak, of axiomatic style mathematics.
Mm-hmm.
You claim, but I think these happen at a much lower level. I mean, you don't need large cardinals to be defining these slices, do you?
No, you don't. It's just that it happens to be the case for historical reasons that the best and the most famous examples of propositions that are independent of ZFC are such propositions. Let's
talk about group theory. Maybe there's easier examples there where things are independent, where basically is it the case? Gosh. I bet there are easier examples there. And I wouldn't be super surprised.
Okay. I mean, you mean like Whitehead's problem and things like that?
I've forgotten what that is. What is that?
It's a question of whether a certain class of abelian groups are necessarily free. And it's you can prove basically by forcing that.
Right. No, I mean something much more elementary than that. I mean something where all we're looking at is the abstract axioms of group theory, where we have not yet given we haven't yet given our relations, so to speak, to specialize to a particular finite group, right? And so what I'm saying is the analogy of this independence thing, there will be much more independent stuff when we have not specialized to that, in the case where we have not specialized, I don't really have this intuition yet. Okay, walk me through this.
Okay, so obviously in the elementary group case, that would, these would be sets of propositions whose word problems are undecidable, but which we can define to be equivalent by additional sets of group relations.
Wait a minute. Wait a minute. What are you saying? You're saying in the case where we have not made, what are the dots in the case of? Yeah, these are propositions. We could think of them as word problems. Basically, every dot here could be a word problem.
Well, you could think of every dot as being a word.
No, I think it's a word problem. I think it's the equivalence of two words.
The equivalence of two words would be connection by an edge.
I think there's a bit of a muddle here, and which we need to come to, and whether these things are the elements of an equation or are each one as an equation.
Right. I mean, that's one thing you said at the beginning that I slightly disagree with, because I thought this is the whole reason why I went through that groupoid construction, was to indicate that it's better to think of them as being terms and paths as being equivalences.
Well, great. That was how I set these things up in the NKS book for thinking about theorem proving. Yeah, I mean, I think that's a clearer way to think about theorem proving. I just am not clear that it works. I don't know exactly how that works. Okay, fine. So they're each words.
Well, so,
okay, I think this is a nice
formal justification here, right? So there's that because of localizability, it's always possible to treat any such multi-way system locally, because the multi-way system is necessarily a topos for reasons I give above. Mm-hmm. And therefore is localizable. And so locally, you can treat it like a groupoid. And so the fact that these arrows are unidirectional ultimately doesn't matter.
Okay, fair enough. We'll come back to this. I think I understand what you're saying. Okay, there's a cliffhanger. I can see the thumb going down there. There's more stuff further down on the thumb. Is that true?
On the thumb? Sorry?
No, and the scroll bar, right?
Oh, right, yes.
There's a lot of stuff. Okay, all right. Can we come out? I think this is a really good analogy, this thing with groups, okay? Where in fact, if you can write some notes, that'd be great. I mean, basically what we're saying is the unequivalenced version of this is just abstract group theory.
Right, as I think I talk about here.
Okay, fine. All right, can we come back to the right-hand side there, where we've got, I'm looking at a much lower level. So, it's abstract group theory. Each dot is a word. Now, when you apply certain group relations, right, when you define a particular group, you can do that by saying additional relations are true, or you can say, I'm going to set up a foliation which makes equivalent these different things.
That's the same thing. The two statements you've just made are equivalent.
I understand, but from the point of view of groups, right, we're saying we're going to define I'm not sure that precisely, I think there's a little bit of a difference here, because one thing is saying that we're going to just assert that a particular word equation is true, which is, I guess, just the relation.
Which is a relation.
Yeah, it's a relation in a group. So, okay. So what we're saying is, with respect to groups, we're saying you can form, you're saying there are a whole bunch of words that are not related. In abstract group theory, we write down all these random words, or in the free group, we write down all these random words, they're just not related, okay?
Right, but we can define, and because they're not related, we can define additional equivalences between them that form group relations, and that reduces the freedom of the model.
Okay, can I, in the case of group theory, this particular picture that you have here, is this in fact a realistic picture? Is the group associativity axiom, for example, could you represent that?
Easily.
What's that?
Yeah, easily. So if we do something like this.
Okay.
Now it's associative. And And we could also add, how do we want to do this? Let's do.
So you claim that is the structure, that every dot there is a word, right?
Right.
And so now a particular group is obtained by adding additional connections in that multi-way graph. Mm-hmm. That's one way to interpret it, right? Or alternatively, to look at it in terms of foliations.
What went wrong? Oh.
I'm not sure what you're trying to do here.
I'm trying to add the identity relation, which I just did. And then I also want to add the inverse relation. So to do that, I can do...
just do that. Right. Okay.
Hey, it's a group.
Okay. So that is a representation of the free group, effectively. Is that right? It has no relations.
Right. Other than the right. So the point is, in this notion of free models, the generator is itself a relation. So in this case, because it does have a generator, that counts as a relation. There is a type constructor in the multi-way system, but there are no relations other than the generator set, which is different to how you'd normally think about it in group presentation theory.
Okay, so wait a minute. So if you label, can you look at this? Can you just label the vertices here? They hopefully they're just words, right? They should be just possible words that have an equivalence.
Right. You see the point that I'm making, right? That in ordinary group theory, in group presentation theory, you make the distinction between relations and generators, but you don't actually have to do that, right? The generator set is just a set of unidirectional multi-way rules, and the relation set is just a set of bidirectional multi-way rules. But all can be considered relations with respect to this more general structure.
So you're saying the generators are, this is a generator of...
Generators are rules that say things like, A goes to AA or whatever. And relations are things that say things like A goes to BA, BA goes to AB.
Right. Although
just that one is unidirectional, one is bidirectional. That's really the only difference.
You're saying you can produce new elements. You can produce new words by these unidirectional things.
Right.
Right. That's reasonable enough. Okay. So then we've got this thing, which is essentially that thing above is a free group, right? If you continued it a long time, that will be a free group, just has all possible words in it, and the only relations in there. Actually, I'm not understanding this. Where is the? There should be relations there that are associativity, and I don't quite understand how you even get that.
That's why we took the transitive closure, right? So
no, I understand, but show me an associativity relation here. I don't see, where is the group multiplication? The group multiplication is concatenation, isn't it?
Yes.
Okay, so where's associativity in that picture?
I don't understand. I mean, if we...
Okay, normally there is a relation in a group that says that, A dot B dot C is the same as A dot B dot C.
Yep, I know what associativity is.
I know.
Yeah.
Okay.
What's the question? The
question is, in what you have there, where those are supposed to be words in the group, right? Yep. How do we see, associativity is simply the statement that all that matters is the sequence of letters. It doesn't matter how that sequence of letters is grouped. Mm-hmm. But yet, what are all these relations that we see here? What are those relations connecting there? Like ABA, there's a relation that says ABBA is connected to ABA. What is that? Because in a free group, I wouldn't expect any relations at all.
But there are relations that are induced by that's the point I've been making, right? There are relations that are induced by the group axioms. The definition of a free group is not one that doesn't obey the group axioms. It's a group that obeys no additional relations beyond those of the group axioms.
Fair enough. But then, okay. So then what we expect, I don't quite understand how this corresponds to, okay, so what will happen here is when we add additional relations, there are two things we can do. We can, if we want to know whether two words are equivalent, and I don't understand equivalence of words here, in that picture there, is it the case that when some word is joined to some other word, that those words are considered equivalent?
If they're joined by a bidirectional rule, yeah.
Fine. Okay, so an example there is ABA is joined by a bidirectional rule to ABBA. How does that work? Because not that is a relation that shouldn't be there in the free group.
Why?
Because the free group doesn't have, there's no reason to think that the word ABA is the same as the word ABBA.
But it's generated by B's. It's generated by applying B's on the right of A's. So you could just apply a B to the right of this A and you get this.
I'm sorry, I'm confused by that statement. What are you saying?
As I said down here, right? The relations and generators are both just particular classes of relations. It just happens to be the case that one is unidirectional, one is bidirectional. So there is a relation that says you can multiply an A on the right by a B. That's what the type constructor was.
Okay, but so in terms of the ordinary presentation of a group, this isn't quite the ordinary presentation of a group.
Well, it's a non-standard group, right? Because normally your generator set would not be this.
But how do we relate this to the standard free group, for example, on two elements?
Oh, well, I mean, we could, right. Sorry, I thought you wanted me to make I thought you were asking about this particular, we started by talking about this particular case, which is the case of generated by this type constructor, which is not the free group on two elements.
All right, let's do the free group on two elements.
So how would that work? Let's think. So it would go A goes to AA, A goes to AB, B goes to BA, B goes to BB, right? Does that seem right?
I think so. I think it'll make a tree, right?
Let's see. Interesting.
Go to it for less steps.
Yeah.
That's really weird.
Cool. But
why are there equivalences?
Why wouldn't there be? Those are equivalences due to associativity, right? We have associativity built in from string concatenation.
Can you label those? Make it just states graph.
Sure. So the string concatenation operator is associative by definition.
Yes.
So we don't have a group. What we have here is what would it be, a monoid?
Yeah, sure.
So we would still need to impose identity and inverse, but this is
no, I understand. But even at the level of a monoid, this is supposed to be a free monoid.
Yep.
Why on earth is that? But the rules of inference here, this is what's so weird. I don't understand. I guess I'm not used to, this is not, I should be thinking of this as, this isn't a Cayley graph. The Cayley graph is a complementary thing to this.
I don't understand your obsession with Cayley graphs, just as a general comment. I mean, we seem to talk about them a lot for reasons I still don't fully understand. The Cayley graphs are useful for specific problems in group presentation theory.
I know. I think they're useful because they're a way of representing what's unique and what doesn't depend on the way they're presented, on the way things are presented. Maybe it's just because they make nice pictures. I don't know.
Okay, that's definitely true.
What? They make nice pictures?
Yes.
What are you doing?
Oh, I should see BY. should be a bit more group-like. Oh,
well,
wait.
okay, but anyway, so look, the main point is that normally these words will just not be connected here.
Right.
Given words will not be connected. But by adding group relations, you make them connected. So really what this is, it's sort of, yeah.
There we go. That's a bit more groupy.
What the heck is that supposed to be?
So all I did was I said, so I added in a character E, which is the identity relation on both elements, X, which is A's inverse, and Y, which is B's inverse. And then just added in the appropriate relations. So this is now a proper, I think, a proper representation of a proper presentation of a group.
Right. Okay, fair enough. Fair enough. Okay, so now the equivalences in this picture has equivalences that correspond to any path connects equivalent elements, right, in this picture. That's what it means to be, the things that are on a path, is that those elements are equivalent.
Right.
Right? So, for example, AX is equivalent to E because X is the inverse of A.
Right. Right. So we can, let's see that.
We see it. It's right there. You can see it. Right there.
I don't trust these graph embeddings. I've been burned too many times by that.
Okay. Well, you can make a more elaborate one. I mean, you could just say something is equivalent to E.
Can we do? Oh no, I didn't get that far. Let's try that.
No, yes, you did. You did. It's just not equivalent to E. Write it out correctly. It's AXX.
Oh yeah. That's true.
AXXA. Well, that should be there.
But it might take more than 3 deduction steps.
Yeah.
This may have been a mistake.
That's okay. All right. Now.
There we go.
Wonderful. Okay. So that shows, that is the proof that AXAX is the identity. Great. Okay. So that's a fact true for any group. Right? So now we could add a relation that says, don't mess up your beautiful group there.
It's going to slow down my notebook if I.
Okay, fine. Okay, all right. So you've got a beautiful group. Now we could say, let's make it an abelian group. We can add a couple more relations. That will add more. Don't change that one. They're good.
No, I'm not. Yeah. So we could say AB goes to BA, BA goes to AB.
Right. Now we have an abelian group. Okay, so now we'll have additional group relations.
Strictly speaking, it's not quite. We need to also add abelianness. We need to add commutativity for E and X and Y, but
yeah, I know.
I can't be bothered.
Right. Okay, I actually have a compiler for these somewhere.
Oh, cool. Okay, that's
repository.
Ideal.
Okay.
Actually, sorry. Pure point of curiosity. If we do a completion on this, do we naturally get an abelian group? I would assume.
Hard to tell. I mean, you can check for abelianness by. Let's see. Why would you get an abelian group? Because why?
I don't know. I was just conjecturing whether. Let's see. Oh, sorry. A, B, 2 steps. Yeah, it gets even more complicated.
And of course, you can recognize that that's an abelian group. No, I have no idea. I mean, we can obviously check it. Why don't we just check a bunch of cases? Why don't we check find shortest path?
Yep. Okay. Completed group.
Okay. So now let's say find shortest path. start off with the most basic AB goes to BA.
Yep.
Humph. I conjecture that the conjecture isn't correct.
It probably isn't. But I'm curious what algebraic structure this is. I'm sure someone in universal algebra must have studied this. It's probably some loop space or something. Oh gosh, that's a bad sign.
Yes. It's a very bad sign. Okay.
Oh dear. Hey.
Oh,
that's
well, interesting. All right, don't destroy that then. Leave it. Okay. We can study that later, but let's just understand. I think this is a really good example because we've got, okay, the thing has laid out in whatever that orthogonal direction to proof time is. We have all these words that are as yet unconnected, all these unrelated words.
Right. Like ABBA in a non-abelian group.
Yes. Okay. So now, as we make we have two choices. We can, as we make a foliation or as we add more relations, we are knitting together, well, what are we doing here? I still don't really completely have this intuition. I mean, so as we put in a foliation, that would be a relation plus a lot of other stuff. A foliation, the typical simple foliation is doing a lot more than just adding one relation.
Right.
It is a very coarse graining of what's going on.
Well, I mean, but the point is that when you add one relation, you are implicitly adding infinitely many. Right.
I agree. And
because
because it's the parallel, it's the forward transport of that relation.
If I say AB goes to BA, that might that might be one relation between two complete states, but AB and BA occur infinitely many times.
Oh, exactly. It's the forward propagation of that relation.
Which is, I mean, that's why completions affect the structure of the multi-way system. And
yes. Yes. Okay. So anyway, but it might or might not be the case that the foliation you make is achievable with a single completion.
Right. And so my claim is that if it is, that's the case of a free model. That's the inertial frame case. Right.
With a single one. I don't know why the one matters. I mean, it's like a small number of them is what I would imagine.
The one matters because to define an inertial frame, you only need an angle. And to define
that is incredibly literal. Are you serious? You actually mean it that literally? That you're basically saying that a velocity vector, you're saying,
you only need to know 2 points in order to define that line.
What's that?
You only need to know 2 points in order to define that line. So you only need one relation, one equivalence.
Yeah, I understand. But the concept that, wow, if that's really right, let me think about that for a second. So you're saying that I think it should just be called I think you call it an inertial model. I would not call it a free model. I don't think it's right to call it a free model. I would call it an inertial model.
Why isn't it right to call it a free model? Because it's free in exactly the same sense that a group is free, right? A group is free because it has only the relation of its generators. And similarly, you have a model that's generated only by a single equivalence. There's no additional relations other than.
Well, you're saying that given that you have the word model there, you're qualifying the word model to say that it is a free model as it is a 2-point model, so to speak, defined by this 2-point relation.
Because it has a single generator, that equivalence, and no additional relations.
You might note my claim that it really should be called an inertial model.
Oh no, I agree that these correspond to inertial frames.
Okay, but anyway, so again, let's go through again this orthogonal direction in the group case.
I have a slightly, I'm reticent to call them inertial models because aren't there, inertia is something that people talk about in group theory, right?
Is it? I don't know.
The people talk about like inertial subgroups in algebraic number theory.
Oh, is that right? I don't know that.
I don't know enough algebraic number theory to know what that means, but I'm pretty sure that is like.
But so okay, so then anyway, we've got these words laid out, and these words are currently unrelated to each other. Okay.
Yep.
Now, by defining a model, by setting up a model, we define relations between these words. The words. It's still bothering me that I don't know what the analog of the term space-like should be for this group. It's kind of like, what is it when you call, as you walk around a free group, so to speak, what are you doing? You know, well, okay.
I don't understand why you, okay, what is your objection to just thinking about them as being independent propositions, which is what they are?
I don't really object to that, except that they are related by the underlying abstract algebra, so to speak. They're not truly independent. I mean, look at them. There is a partial order between them.
Wait, what? No. The whole point is there isn't a partial. Wait, but you mean between like these two?
No, the anti-chain. All right, we're trying to name the anti-chain, and
the whole point of the anti-chain is there isn't a partial order between them.
Well, I understand.
The order is partial precisely because it doesn't.
The anti-chain is space.
Yeah.
And the reason that
and in proof time, the anti-chains are undecidable propositions.
Are undecidable. Well, we should be careful about the term undecidable. Are undetermined. I mean, undecidable tends to have this meaning of infinite path length and things. They are the
But you can interpret space-like separated points as ones that are connected by infinite length time-like vectors, if you wanted to, if you were sufficiently perverse.
But similarly, I mean, it's just like undecidability is a little bit, you know, as people understand it from Gödel's theorem and so on, it's just as a brand name tends to mean more than just.
Right. That's why I'm using independence in the logic sense, right? That they are independent of the axioms. They are an anti-chain.
All right. So really, what this is it's the independence direction in some sense.
Right.
This direction, space-like separated are independent. Yeah. Okay.
A pair of points is space-like separated.
If they are independent.
Well, if they correspond to a proposition that is independent of the axioms.
Right. If that relation, if the relation between them is a proposition independent of the axioms.
Yeah.
Okay. All right. Okay. One more push at the constructivism, and then we're going to get back to what you really want to talk about, and I apologize there.
No, that's no problem.
Okay, and actually there are questions on our live stream that are kind of interesting here, like from Jose. Any theorem that can be proved in finite time is in our computational event horizon. Yes, absolutely.
Right. But the point is there will be statements that are at the computational event horizon, which are the kind of those are the limit points where things become non-constructive.
Right, where the only way to reach them, there's no way to reach them by models, because the models would have to be, would take infinite verification time to establish.
Right.
And therefore, the only way to reach them is by, that's, I think, a good way to say
it. I agree that is a good way to say it. So a model moving along a time-like path is not constructible because constructing / verifying it would require infinite computational effort.
Right. So the non-constructive, what is interesting about this is that the non-constructive propositions are a boundary.
Yeah.
Isn't that kind of interesting?
It is.
Could you write that down just so we don't forget it? I mean,
didn't we already say that? I mean, it's the boundary of this cone.
Well, I know we said that there, but the general point that in general, that non-constructivism is a boundary effect.
Non-constructive.
So non-constructivism is that's very interesting. I mean, non-constructivism is just before you reach independence, basically.
Right. They're time-like paths.
I know, but is that obvious from other things we know in mathematics, that non-constructive stuff? I mean, it seems intuitively right.
That's why I kind of brought it up, right? Because I think it is a non-trivial realization.
Right. The non-constructivism is the edge. And as you go beyond non-constructivism, you hit independence. That's actually really quite interesting in my view. How does that relate to what's known about constructive mathematics and so on? Is that surprising? That, I mean, yeah, I mean, what we haven't addressed here is things which have traditional Gödel-like undecidability, where there's an infinite proof chain necessary to get to it. How does that relate to this? So that's something. For there to be an infinite proof chain.
I'm confused. Didn't we kind of discuss this? I mean, so in the case where you have this is a bad example because this multi-way system obviously isn't capable of universal computation. But if you have a non-trivial multi-way system, knowing whether a pair of points
absolutely is arbitrarily
independent is arbitrarily hard. I mean, that's the analog, isn't it?
It is the analog. Yeah, that is the analog. Well-known analog, right? But the question is how that relates to this non-constructivism, and that's not so clear to me. How that relates to the construction of models, so to speak. The presence of that arbitrary difficulty, what that corresponds to in terms of models is that you have to have an arbitrarily squiggly model to be able to capture that effect that takes an arbitrary amount of time to determine equivalence, says that to burn that into a model would require a model with an arbitrary, serpentine, this is the, oh gosh, what is the word? What on earth is it called? How can I have lost that word? The word for districting, for
gerrymandering.
Gerrymandering, thank you.
Yeah.
An arbitrarily gerrymandered, in order to make a model that correctly, you're going to the limit of infinite gerrymandering, so to speak, to make a model that successfully captures the things which would be otherwise infinite proof chains.
Right.
Okay, so a question here, we have a couple of questions here. What is Hawking radiation in this framework? Yeah, model theoretic gerrymandering.
Model theoretic gerrymandering may be related to inability to construct. We kind of discussed this last time. Things like Malamud-Hogarth spacetimes.
Yes. They are non-constructive.
Yeah, i.e. they would permit, well, in both cases, hypercomputation would be required on the part of the observer.
Right. So the point is that hypercomputation, actually, that's an important point, which is not a totally obvious point, which is this is saying that non-constructivism is hypercomputation. Right? That's the most important point here. That is the relationship between, standard proof stuff is saying that the merely computational in mathematics, that is kind of the obvious feature of constructive mathematics, is that you can compute things in constructive mathematics. Whereas this is kind of highlighting the fact that non-constructive mathematics, things that live on these light cones, is a
corresponds to hypercomputation.
Is what?
Corresponds to hypercomputation.
Yes, right. So that non-constructivism equals hypercomputation, basically.
Right, exactly.
Which is what we kind of thought was true, but this is a nice way of making that explicit.
Right.
Do we care about volumes of geodesic balls and things in these systems?
I would say so, in the sense that implicitly tell you about deflection of proof paths and things.
Yeah, but what is that? What is the significance of that? And what is the significance of
well, I mean, so like we can make, I mean, so for instance, if we do something like this, we could say, so if we take, I don't know if this might produce something totally trivial, but let's try it anyway. Is that commutativity? Oops. From axioms.
Even though there's only one of it.
Right. It's for consistency. It's for naming convention consistency with the rest of the axioms. Okay. So now we have a look at the proof data set. Okay, so if we took, okay, so that's what our first proof graph looks like. But we can make some elementary, so this corresponds to a geodesic, right?
What corresponds? This whole proof graph is a geodesic in the multi-way system, and it will be lovely to draw the whole multi-way system for this. Are we capable of doing that? I mean, not for this one, it's way too big, but even in a simpler case, this is a question that I wanted to ask, is those stubs.
Can you construct an inverse of fine string proof effectively? Right.
One way to look at it, yeah. I mean, can you do something which gives the whole, this is a slice. Mm-hmm. And in this slice, I mean, one thing that's confusing me in this slice is the presence of causal edges. Should I be confused by that? No, I mean,
so look, here's what's happening, right? Here's how the representation works. So if we take one of these multi-way systems, we do say evolution causal graph structure, right? So we have a bunch of these causal edges. Then what we're seeing is if we take okay. So if let's call this multi-way graph. So let's prove a proposition like ABAB ABAB goes to ABBB ABB or something. Mm-hmm. Actually, that's maybe a bit too simple. Let's do something like that. So that would be one path. But what?
Oh, hold on, I was not paying full attention here. So what's happened here?
Okay, so hang on. Nothing has happened so far. It's okay. All I'm going to do, I think, is this right? This is how you get all paths. Yeah. Okay. So then so this is the overall multi-way causal graph. So if I look at the subgraph of the multi-way causal graph, or the evolution causal graph induced by those paths, I would see, oh, that's kind of boring.
I think you need longer strings to be able to see more causal edges.
Yeah, right. No, but what I also want to see is non-trivial branching, which I'm currently not seeing. Hang on. Wait, let me go back to. Let me try this with the states graph structure, and then we can build up. So if I do that.
Are you basically going to claim
there's only one path?
Go ahead.
That's rubbish. Okay, sorry. Wait. Does this not work? If I do find path infinity all, that should produce all paths, right?
Look at the documentation. I don't remember. I'll look at it.
Find at most n paths. Yeah, so if I do k-spec infinity all.
Yeah, it should find
all paths.
Yeah.
Was there really only one path? That seems improbable. Okay.
From where to where? Well, just do the top.
Oh, okay, oh, right, finally. Okay, so we've got one that has multiple. So if I do multi-way graph, subgraph of that. Okay, so there's a collection of geodesics. So if I did highlight graph, multi-way graph, subgraph.
Great.
Okay, wait. Oh, that's probably why I just chose a really boring proposition. Let me choose a more interesting one.
Choose one which has bigger area.
Just right.
Choose one.
ABBB, ABBB. Oh, I could do like probably do this, right? No. Yes.
Okay. No,
that might just be the whole graph. Okay. Is that too much?
I don't know. It depends what you're going to do.
Okay, so
that sounds fine.
Okay, so that's a collection of GD6, right?
Yep.
That produce this thing here.
Yep.
So then what I want to do is actually I want to get the evolution causal graph structure.
Okay.
And I want to get the associated paths there. I can do highlight graph. That's our geodesic collection, our geodesic bundle that corresponds to this thing here. So it's this geodesic bundle that the proof graph is representing. And all you're saying is
wait. The whole geodesic bundle, why is it representing all those paths? I thought it was just representing a single geodesic.
So it is, right? So what it's doing is for every bifurcation in this geodesic bundle, so if we take...
Oh, it's stubbing it.
Right, it's stubbing it down so that there's just a single triangle. Okay, so what you end up with, up to the equivalences defined by the triangles, what you end up with is a single geodesic. But what you started with was a whole bundle of geodesics.
Okay, let me just internalize that. So you're saying those triangles.
So that, yeah, if I do this with multi-way states graph.
You're saying you're summarizing it by going only one way on what would otherwise, I mean, those are equivalent. Is that right? The different geodesics are equivalent.
Exactly. So
there's a way of modding it down by that equivalence.
Precisely. So the point is, because these are all derived from one common expression by valid application of the rewrite rules, all of these things that lie on the same hypersurface are equivalent with respect to the rewrite relation.
Yes.
Right? So anytime there exists a bifurcation, which I guess we could get vertex, select vertex degree.
It's going to be everything. It's going to be everything.
Can I not do that?
What is that? Vertex degree.
Oh,
greater than 1 is going to be You're going to have to do it for each individual vertex. You're going to have to map the vertex degree.
Oh, never mind. You get my point, right? So for each bifurcation, there is
each bifurcation. You only need to follow one path.
Right. So all that's happening is every time there is a bifurcation, rather than showing the other path, we're just going to show a triangle.
Lovely. That's nice. It was good notation. Wow. How prescient.
Right.
I mean, I remember we did think about those triangles as being, but that's good. Okay. So every one of those, just to understand, actually the triangles are the wrong way up. Is that not correct?
Well, you could think about them as, they are kind of the right way up, right? Because it's like this would be a bifurcation here.
Okay, but is it true that those are causal edges? I don't think they're causal edges.
What, the dashed lines?
Yeah.
Yes. Or they're as close to causal edges as you can get without actually being causal edges.
What do you mean by that? So can we actually make that picture? I mean, if we would do this for the strings. We should do this for the strings case.
Yeah. I mean that's on the to-do list. Don't worry.
Okay, fine. Okay, in the strings case. Okay, so let me just understand then what we have. So in this proof.
So what these causal edges are showing you. If we let's do it small enough, we could actually look at the full evolution causal graph, right? So there is an element here that was produced that you're applying a rule to that was produced by this previous event.
Yep.
Right. So similarly, when we have one of these dashed lines, that's where we're using, I mean, we can see this explicitly if we look at the proof data set. And I probably should have proved a less absurdly complicated proposition to show this off. But where you have one of those dashed lines, that's where there's Oh, critical pair lemma is a bad example. Let me do a substitution lemma. It's easier to understand. So there is an input thing. That's the expression that you're applying the rule to.
Yep.
There's also a construct, which is where did that rule actually come from? Why is that rule applicable? And that construct is a previously proved thing.
Yes.
So effectively, the fact that that construct is applicable, you can think of as being directly analogous to the fact that this rule was applicable only because there was this previous rule that got applied.
So it's a causal edge. So whenever you're feeding something in to be applied, it is related by a causal edge to wherever it came from, which might have been the Big Bang.
Yes, right. Which in this case would just be the axiom.
Right.
And then the critical pair lemmas are exactly these bifurcations, because if we look in here, it's saying here's a pair of constructs that happen to be the same, axiom 1, inducing the same pair of rewrite rules, but for a given subpattern, they produce different results. They produce different, there are two different ways that you could apply this rule to this subpattern in such a way as to get different results. And those are the two different sides of this critical pair lemma. So
do we learn anything about our general display of multi-way systems by this? In other words, this kind of approach of stubbing the branch hill direction. Did we learn something?
I think it's worth. So one of the things I kind of want to do reasonably soon is just write a converter to and from proof objects and multi-way systems.
Yes.
We've got some of that already with fine string proof, but I think it's both useful. It happens to be the case we designed the proof object before, or at least before I really understood the significance of multi-way systems. And if we'd understood what we understand now, we might have designed this a bit differently. But so I think it would be useful to be able to visualize these as multi-way systems. But I think, as you say, equivalently, would be nice to be able to visualize multi-way systems.
Yeah, the reason, I did understand a little bit more. The reason I didn't push harder on that is because I thought that the actual application of the rules in these tree structures was something much more complicated than. Right. In other words, that a lot of the story was in the application of the rules to the tree structures.
Right. So in fact, actually, hang on, we could. As just a quick hack. This is the multi-way system representation. This is the proof graph representation. We can put those side by side. I don't know if that's useful, but
it'd be more useful if we labeled everything, and if you had my code for labeling the strings.
Oh, okay. Well, yeah, we can.
But let's walk through that. What corresponds to what there?
So the point is, there's actually, even though it appears there's multiple bifurcations, they are all just particular instances of the same bifurcation, right?
What happens if we put causal edges into that left-hand side one?
Well, we get whatever complicated thing we got up here, right? So we could do.
But those causal edges are significant, right? They are things that appear in the right-hand side proof graph.
Yeah. Okay. So let's do that. And just so it's a little bit less rubbish, let's do. Oh, did I call that rep 2? That was terrible of me. I should have called that. That was rep 2.
Yeah, it was rep 2.
This is rep 1.
Okay.
So then let's do layered half plot. Rep.
Oh.
Is that helpful?
Well, do aspect ratio to whatever.
Oh, yeah. Is aspect ratio half is the one you like, right?
Well, it better be the case that one of those black lines corresponds to the solid thing, right?
Yes, right. Right.
We should trace this more carefully. But let's go to the point. Okay, this comparison is useful though, because we're going to talk about both, general relativity and quantum mechanics in this connection. That is, what does it mean? The quantum mechanics of mathematical proof is this idea of multiple proof paths.
Right, it's proof redundancy.
Right.
Mathematics is sufficiently rich that there exist multiple proofs of. Yeah.
Right. But the fact that there is a meaningful objective reality in effect is a causal invariance type statement. Yes. Yes. Well, or there's causal invariance in the underlying rules. We don't know yet.
Oh, sure. But I mean, well, yes. The same could be true in mathematics. Oh, sorry. The point is, in either case, if it is causal invariant, it takes enough time to achieve causal invariance that it might as well not be.
Well, that's an uncertainty principle statement, isn't it? I mean, in other words, if the so you're saying the univalence axiom, which is, and I need to understand more of the details of this, but basically the point is the univalence axiom, aka extensionality axioms, et cetera, is this coarse graining axiom that says you can throw away the working. Right. Basically the statement that in mathematics, all we care about is what's equivalent, not how it got there.
Right.
By the way, we have a number of comments on our live stream here. Oh yeah, Jose is pointing out here that the dimensions in space correspond to the axioms, the number of axioms. That's a good point. Or the number of independent propositions, which is kind of like the bag of axioms, which is kind of like in Greg Chaitin's algorithmic information theory way of thinking about mathematics. It's kind of like those are the things those are the sort of randomly different, undeducible things. Right?
Right.
So in other words, you throw in this giant bag of axioms. And
well, yeah, I mean,
what's that?
Proof theoretic independence is linear independence in the resultant space. Right. Each independent proposition is defining a linearly independent vector.
That's true. Well, yeah, in the sense of dimensions of that sense. But what I'm just thinking about is just the way of thinking about having. Yeah, I mean, so this is just saying, I should have realized this before. I mean, this thing about having all these things be independent is just talking about whether they are sort of separately, it's this pi versus omega business. Okay, I understand that. Measuring fractal dimension will be a way of determining whether something is undecidable. I don't know about that. Okay, John is observing the non-constructivist limit would be the Cauchy horizon.
Yeah, well, it would be a Cauchy horizon.
Why isn't it any Cauchy horizon?
Well, it is, yeah.
Okay, so and whenever there is such a horizon,
but the point there isn't just necessarily saying the Cauchy horizon makes it sound like it's guaranteed to be unique, but that isn't the case in relativity. I don't think it's the case in mathematics.
What's that?
It certainly isn't true in relativity, and I don't think it's the case in mathematics either.
Right, but the main point is that as you walk through mathematical space or mathematical proposition space, you will visit propositions. The question is, is it obvious that there's this boundary, this non-constructivist boundary, where you basically go, there are certain sequences you couldn't have, right? You can go, the question is, okay, here's a question. Does every decidable thing have a non-constructivist border before you reach independence?
Right.
Remind me what would the strong cosmic censorship. Weak cosmic censorship is just the lack of the fact that there's an event horizon around every singularity.
Right, there are no naked singularities. The strong cosmic censorship conjecture is the statement that there exists a well-posed Cauchy problem for the Einstein equations, that the Einstein equations are deterministic in the hyperbolic sense. So the existence of a Cauchy surface is the statement that there exist mutually independent propositions.
Sorry, the existence of a Cauchy surface or the non-existence of a Cauchy surface? The non-existence of a Cauchy surface. What's that?
The existence of a Cauchy, the existence of a Cauchy surface, on which you can define initial data, and the time evolution problem is well defined.
And it doesn't get tangled up. Basically, you can define those independent things, and they stay independent. Is what you're claiming.
Right.
So a Cauchy problem,
a collection of space-like separated points,
or a collection of independent axioms that don't tangle themselves up, of independent axioms.
Intersects.
So the question is, can you define independent axioms which will not tangle themselves up? That's the issue. That's the analog of this.
Yeah, exactly.
You should write that down, just so we.
But that's the first incompleteness theorem. I did write that down.
Okay. Jose is asking about the interpretation of Goodstein's theorem.
Well, it's just an example of an undecidable proposition, right? I don't think it necessarily has any
sequences are. I don't know what the
Goodstein's theorem is the statement that Goodstein sequences terminate. So Goodstein's theorem is decidable in ZFC but undecidable in piano. That's the whole Kirby-Paris.
Right. Okay, so what in this case, what is the analog here? What's the analog of that? Of saying that when you add additional axioms, something becomes decidable. What is that? What is that picture? That's again this whole story about foliations. It's the same story again.
Not really. I mean, so what you're saying is you could extend your partial order so that things that would otherwise have been independent are now related by the order relation.
Oh, that's the same thing as saying you're adding relations. Right?
Yes, but the question is, but the question is, are you adding the relations at the level of the proof theory, or are you adding them at the level of the model theory?
Absolutely, right.
And so in this case, you're adding them at the level of the proof theory. So it's nothing to do with the foliations. It's to do with extending the partial order without foliating.
Indeed. But so then the question is, okay, but let's understand the relation between those two things, because we've argued that by adding a relation, that is defining a frame, basically.
Right. Models can simulate stronger axiom systems.
Yes. Right. Within reason, but they have certain limitations, because stronger axiom systems can have a level of squiggliness that the stronger axiom system can lead to things that are not well represented by computationally bounded foliations.
Right, but you are still computationally bounded.
All right, now we're horribly over time, but let's go back to what you originally wanted to talk about here.
Yes, I feel bad. Xerxes has been essentially silent in this entire stream.
Oh gosh, I have one more question, which is the sort of the quantum. Can we in fact nail down this question about general relativity and quantum mechanics here?
I thought so. Yeah.
Well, what's the analog of Einstein's equations?
Well, I mean, this is originally we got distracted, but this is originally why I set this thing up, right? Because what I was going to show was, sorry, my notebook is slowing down. There's too many big things in it. What I was going to try to show was the analog of geodesic perturbation. Which I think we can do. So so proof 1 has 102 steps. So if we take, but if we do proof 1, proof data set 3.
Yep.
Statement. So what we're basically doing, what I want to do is you know, we have some geodesic, but what I want to try to do is to pull back, you know, 1 point on the geodesic a little bit. So just take 1 point on the geodesic and perturb it.
Yep.
Right. So I can do that by just adding in an axiom that is one of the statements I would have proved along the way anyway. So if I do that, so if I do join axiomatic theory, Wolfram axioms, what this thing?
Oh, you know, you had your commutativity thing. First argument has to be the commutativity.
No. I know. I'm filling in the axioms first.
Okay.
Yeah. Okay. That's all good.
Why don't you just copy it from above?
I'm scared to scroll through this notebook now.
Okay.
Oops. What did I get wrong? Oh, this should be a list.
You don't want to join, yeah.
Oh, and I actually want to call this proof 2. And we might get something completely boring, or we might not. But what I want to try to do is to put the 2 proof graphs together. Oh, we did get something completely boring. Oh!
It's on the way. That's the problem.
No. I know what the problem is. Yeah. The problem is implicit versus explicit quantification. That should make it shorter. If it doesn't, something has gone wrong.
Yeah, well, but the fact that it's on the way, doesn't that bother you? Because it's not going to make a different geodesic.
No, but it should, right? So it wouldn't if the Einstein equations didn't hold. The point I'm trying to make is because we have Einstein equations.
Oh, yeah, let's see the result.
When you
before you comment.
Yeah, you get subtly different proof graphs.
Well, it's hard to tell from the embedding. But yes, you're saying just because it's on the way, if it was flat space, you would just keep going on the same line.
Right.
Because it isn't flat space. There's a shortcut.
Right, and we can see that it's not flat space because of the presence of critical pair lemmas, right? Each one of which is indicating a non-trivial holonomy in proof space.
I guess so. That's a little less obvious to me.
Well, because each critical pair lemma is an indication that there is an elementary triangle in the associated, in the full multi-way proof network, in which the direction along which you transport matters. So they're the analogs of discrete, elementary holonomies. And so but
in the branchial direction, not in the space-time direction.
Sure.
So it's not self-evident that would lead to something non-trivial in the pure space-time direction.
But we can define the analog of a Riemann Riemann curvature tensor on that space.
On which space?
On the induced, on the branchial space.
Sure, we can. Right, but
so you can still compute, the commutator of the covariant derivative.
No, I understand, but that's in the quantum mechanics case, whereas what you're trying to show here is the general relativity case.
Well, I mean, they're the same, right? I mean, they're
in some generalized sense of sameness. Okay, okay, so the claim here is that this fact that, okay, so let's just review what you're saying. You're saying that the shortest proof you get, that even if you use one of the things which is an intermediate point along a proof, you actually can get a shorter proof, and that's a reflection of the non-flatness of space-time.
Let's see.
Proof.
Well, I mean, let me try and prove myself wrong. So this should be a flat space-time, right? There should be no critical pair lemmas here.
Yeah, okay.
So if I now so substitution number 1 is element 5. Okay, so then if I do find equational proof of A equals D, oop. Yeah, okay, so we got 8 steps because there's one additional axiom, but otherwise we didn't change the length of the proof, right? The proof is...
I don't understand why the critical pairs that seem to go off in a branchial direction affect the structure of what's effectively space-time.
What do you mean the structures? The branchial direction is our space, right? So all I'm saying is...
I see what you're saying. I see what you're saying. I see what you're saying.
There's curvature in the associated space. So
yes.
Unlike in the flat space case, when we perturb the geodesic a small amount, there's a non-trivial effect on the length of that geodesic. That is
right. So this is saying
a byproduct of the Riemann curvature.
The statement that there is curvature in proof space is the statement that the shortest path between 2 points in proof space,
right,
is not necessarily, in other words, if you pick an intermediate point in a proof, it is not the case that the shortest way to get the proof always go, you get the, you're going to say the point, but okay, so the statement is that in mathematics, so probably it should be the case that the density of what is this non-directness? This non-directness is saying proving A if you go from A to B to C, I'm a little confused by this. You're going from A to B to C, and now we're looking at purely B to C. Well, the claim is that the distance A to B plus B to C is not equal to A to C. That's the basic point.
Right. As witnessed by the fact that if we try to, if we treat this as being like one way around an elementary triangle and this as being like another way around an elementary triangle, we get to slightly different points because this critical pair doesn't immediately converge. So this is an example of a non-trivial holonomy, whereas, this would be an example of a trivial holonomy. And the important point is this is the case where you would induce a critical pair lemma. So the density of critical pair lemmas is an analog of the, is allowing you to deduce things about the Riemann curvature. Okay, so this is something we're familiar with in quantum mechanics, basically. Right. This is the uncertainty principle. Just like it's all just statements of non-commutativity, right? Riemann curvature is a statement of non-commutativity of covariant derivatives. Quantum mechanics uncertainty principle is just a statement of non-commutativity of measurement. Critical pair lemmas are just a statement of non-commutativity of proof steps. Right. So the basic point is the analog of general relativity in proof space is the statement that it is that a waypoint in a proof, that there may be a more direct path or a less direct path than going through that waypoint.
What does that mean qualitatively for the practice of mathematics? That it's faster, that the existence of waypoints and the question of how much curvature there is depends on this density of causal edges, right?
Well, that's the Einstein equations, right? It's telling you that there's a coupling between the Riemann curvature and the energy momentum tensor.
I know that, but so what's the significance for mathematics of the fact that the presence of causal edges, of causal edges is telling you that it either is or isn't a good idea to go through that waypoint.
Well, look, here's the point, right? So each critical pair lemma is an indication of the requirement for mathematical creativity at some level. If there were if you have a case like this, there is no creativity required on the part of the mathematician. The mathematician just starts from the axioms and just robotically applies substitutions, right?
Yes.
But the point is, if there are critical pair lemmas, suddenly it matters, which axioms you apply and when and to what propositions and things. So that, the more of these critical pair lemmas there are, the more creativity you need to be able to prove theorems. And the way that automated theorem proving algorithms work is by adding these critical pair lemmas in the hopes that if you add enough of them, you eventually don't need any more creativity. You can just robotically apply substitutions. So what this is really saying is that the more, so each of these causal edges, like I say, is kind of like a new layer in some tower of abstraction, right? It's the statement that the new results you're proving depend on some previous results you have to understand first.
Yes.
And so what the sort of metamathematical claim is that the higher the tower of your abstraction, the more creativity you need in order to be able to prove theorems, which is kind of, we expect to be true anyway, right? I mean,
okay, let's walk through that for one more time. So the claim is the higher the tower is rather the density of causal edges, which is
right. I.e. the more dependence on previous.
What's that?
Yeah, the more dependence on prior results. Yeah, I guess it's not necessarily higher, right?
It's just
not. The amount of abstraction. The greater.
Well, the more dependence on previous results, I think, is the right way to say it.
Okay.
Because I don't think it's necessarily the right measure of abstraction. Okay, greater the dependence on previous results, the more creativity is required to prove theorems, and the reason for that,
which is kind of obvious, right? Because there's more, there's greater choice,
possibilities,
of things to do.
Well,
right?
okay.
The more technical machinery you have in your arsenal, the more stuff you can do, and therefore the more creativity you need in order to.
Well, the more possibilities there are to go off track.
Right, right.
The more this is really the more tools to go in different directions that you have, the more you can go in the wrong direction.
It's probably a bad example. If you can only do one thing, you either prove the theorem or you don't.
Right. I mean, it's a question of how much branching there is. Okay. So, but there's probably a quantitative result here.
Yes. Right.
The quantitative result is, given a certain bag of axioms, so to speak, a bag of previous results,
and I mean, this is something we can prove empirically just by running automated theorem proving tests.
Which?
The statement. I mean, so if we wanted to, we could enumerate all possible axiomatic systems, as you've been doing for 30 years or something, and we could just plot the relationship between the density of causal edges and the density of critical pair lemmas, which I'm pretty sure no one's ever done before.
Yeah.
And from that, we should be able to deduce effectively what's the coupling between the energy momentum term and the Riemann curvature term.
In this particular theorem prover.
Yes, right. Which will correspond to one particular geometrization of proof space.
Okay, so what does that mean? So the coupling between the energy momentum tensor, so we are deriving, for this theorem prover, we are deriving the value of G.
Well, it's not necessarily the value of G. It's what we're empirically deriving the full Einstein equations, right?
Well, we're deriving the relationship between T mu nu and the curvature tensor.
But the Riemann curvature tensor, right? And so what we would expect to find is that there's some redundancy, that, that there are some directions where the density of critical pair lemmas doesn't matter, that which will correspond to us taking a trace. So what we should, if the analogy with the Einstein equations is perfect, then we should expect that there's enough redundancy that you can effectively trace out and end up with the pure Ricci curvature tensor.
And what does the bundle of GD6? What does the cross-sectional area of the bundle of GD6 correspond to?
Well, that's the critical pair lemmas, right? Because if you remember up here, right? So each
exactly, that's the amount of redundancy.
Yeah, it is the fatter this thing is, the more critical pair lemmas there are by definition.
Right, but so which way round is this working? So it's saying the more energy there is. This is actually the opposite way around from the Einstein equations, right? The more energy there is, the less concentrated the GD6 are.
Yeah. Hang on. Let's see. Is that right? Or in other words,
same as in branchial space, because the more energy there is, the more it turns the path integral.
So in other words, this behaves more like vacuum energy than it does like positive energy momentum, which is interesting.
I think so, but I mean, isn't that the same as the Lagrangian in quantum?
Yeah, no, I agree. I'd never internalized that before. So dependence, energy momentum as dependence on prior results, just as energy momentum as Lagrangian intensity,
right,
in QM is more like vacuum energy than baryonic matter.
Right.
Behaves more like.
So in other words, this causes negative curvature, basically. The presence of previous knowledge sprays out your GD6.
Actually, yeah, that's kind of obvious that it behaves like vacuum energy, right? Because we don't have, neither in the proof case nor in the QM case have we considered the presence of topological obstructions, which presumably work the other way around.
That's true.
All we have is vacuum energy. Yeah, okay. So this is actually an obvious, right?
On the other hand, the question that then raises is, what is the analog of topological obstruction in branchial space?
Well, quite. We aren't considering topological obstructions yet.
What the heck are topological obstructions in this
proof space? That's
proof space. They're going to be some crazy homotopy thing in your crazy infinity groupoid weirdness.
So yeah, I mean, let's think about that for a second. So, No, okay, I don't. I have no intuition for this.
Well, but so basically, what we're saying here is the constant of proportionality between number of amount known, tool set, and ambiguity. That's the constant of proportionality that we're dealing with, which is the analog of some H bar G type thing.
Right.
Okay. And what we're saying then is that right, we should be able to measure a bunch of these things. And this is kind of an empirical metamathematics of automated theorem provers. There's a different empirical metamathematics of what humans do.
Much harder, because humans aren't very formal.
Well, I know, but I've made these plots for like Euclid's elements, okay, of at least what theorem follows from what other theorem.
Right, but that's not good enough for us, right? We need to know where the ambiguities lie, and human.
No, I know, because that's only one proof, right? That's only ever one proof that's given. This is looking at all possible proofs.
Right, but even looking at all possible proofs isn't you need to look at all possible proofs and then look at the geometry of the induced network.
Yes. All right, let's go back to what you originally wanted to talk about here. I'm sorry.
No, that's okay. Well, fortunately, the thing I want to talk about is not very complicated, so we might be able to just crack it immediately. It's just,
okay.
And actually, both you and Xerxes may have realized this already. I may have just been slow. But I think it's kind of cool because I think we have a new way of thinking about what a tensor product is. Or at least there's a way of thinking about what a tensor product is that I hadn't realized before.
Well, wait a second. The thing we get before even we get to any of that stuff is this situation that we're talking about is a specific axiom system, right? We're talking about a specific axiom system that we have been doing so far. But we can also go to the rule space limit, so to speak, where we're looking at all possible axiom systems.
Right. So to remind you of what that looks like. So this is a rule space of, well, actually it's a cheating section of rule space of all possible axiom systems if you were to represent them using Turing machines.
Okay, I think it's probably better to do the string version of that, which I also had a picture of somewhere.
Right.
Okay.
Okay, yeah. So then the point is, what we can do is we can start constructing foliations of that, and the point that Xerxes, okay, so categorical quantum mechanics, as I think we discussed this the other day, but let me just very quickly.
Make that a section heading.
So categorical quantum mechanics, Koka and Abramsky.
Yep.
States, okay, so QM can be done in a symmetric monoidal category. i.e. a category equipped with a bifunctor interpreted as a tensor product with an additional left and right identity object for the bifunctor, and where this bifunctor is as commutative as possible.
So a functor is a mapping from one category to another, yes?
Yes, right. Okay, so functor maps from one category to another.
Within a category, there are a bunch of morphisms, and the functor is mapping from one category to another.
Right, exactly. So bifunctor maps from two categories to one.
Oh, really? Okay, I was thinking it was going a two-way functor. Okay.
No,
okay.
So the idea is, you have your category, your category is C.
Yeah, I get it. Yeah. I get it. It's a function with two arguments, basically.
Yeah, exactly. So the idea is you can equip your category with a bifunctor, and then you want that bifunctor to be as commutative as it can be. And the point is that naturally generalizes things like tensor product spaces, or but it naturally generalizes things like modules and algebras and other kinds of things that have tensor product structure. So the idea of Koka and Abramsky is that you could do QM inside this symmetric monodal category, where that where you're so effectively you're doing quantum mechanics in some generalization of the notion of a tensor product of a collection of finite dimensional Hilbert spaces. Right, that's the idea.
What does it mean to do quantum mechanics in anything?
What do you mean? I mean, so you have to have some background structure in which you're defining, with respect to which you're defining your states and your operators and things, right?
Okay.
So in ordinary QM, you would say that's a Hilbert space, or I'd say in the case of a more complicated system, it's a tensor product of finite dimensional Hilbert spaces.
Yep.
And so categorical QM is just saying, well, instead of doing that, we can generalize that to the symmetric monodal category object.
Lovely. Okay.
Okay. That's the basic idea. So Xerxes' idea was, if we consider taking a multi-way Turing machine, so well, actually, we can just. Do I still have? Oh, I still have rule graphs. Oh no. What I actually want to do is this. Let me start off pessimistic and just run for one step. What I want to get is some branch Hill graph structure. So I'm taking this section of rule space and I'm foliating it.
Yep.
And but then the point is for any individual NDT. So as we discussed last time, right? For any individual NDTM, can be interpreted as a fiber in this rulal space. So if we fibrate the space, we get this individual fiber like this. This is a particular NDTM in this rulal space. And it is a legitimate fiber because it has this homotopy lifting property. So if we define a homotopy between paths in this base space, it lifts to a homotopy between paths in the associated fiber bundle. Okay, so then the idea would be if we foliate the rulal multi-way system versus if we foliate the individual NDTM, the idea would be that the rulal multi-way system is the branch-like hypersurfaces that you see by foliating the rulal multi-way system can be interpreted as this generalized tensor product of the branch-like hypersurfaces that you would see by foliating the individual NDTM multi-way systems.
Okay.
And so therefore, if that conjecture is true, then Xerxes pointed out that basically we immediately have that our model of quantum mechanics is immediately compatible with categorical quantum mechanics, right? Again, Xerxes, please, is this a legitimate statement of your?
Yeah.
Okay. Please feel free to interrupt me if I say anything or if you want to add anything, or you think I've said something silly. So that I think is kind of interesting, right? Because it means that the composition of these individual constructors for multi-way systems is the analog of a generalized tensor product. And similarly, the fibration of a higher order, say a rulal multi-way system into individual multi-way systems is the generalization of a partial trace operation, which maybe we already knew, but I at least thought was kind of cool because I'd never really thought about it that way before.
Okay, just zooming. I'm sorry, I'm still looping on some other things here. I mean, basically, we're saying, I'm still looping on the kind of the whole univalence axiom, rulal space, etc. But you were about to show something else. I mean,
what I want to try to show is a more explicit example of what I mean. Okay, so if we take, space one is this multi-way system, we can construct its associated branchial space. If we do space two, we can construct its associated branchial space. Okay, so then the idea would be, now let's do the higher order multi-way system that contains both rules. So A goes to BA. And so then we could do a highlight graph of subgraph. Let's call this TP object. Then if I do highlight graph TP object, subgraph object, let's do object one, subgraph TP object. Two. Okay, so then you can see these are the individual objects from which we construct. These are the individual multi-way systems from which we then kind of multiplied together in some generalized sense to obtain this higher order multi-way system.
Okay.
Right.
Yep.
And so then if we take this higher order gadget and we foliate it, construct its branchial graphs, we get this much richer structure. But within this richer structure, so let's call this TP space, tensor product space, highlight graph, TP space, subgraph, TP space, space one, subgraph, TP space, space two. Wait, did I not call it space two? I called them both space one because I am incompetent. I'm very bad with these variable names. Okay.
No, that's why we're trying to build an auto-suggestive of variable names, which doesn't have a hope in hell of being able to catch all of these. But anyway,
that sounds like an undecidable problem. Right. Okay. So here we have two individual spaces, right? Which we're interpreting. If our model of quantum mechanics is right, these are projective Hilbert spaces in general. two individual spaces which we've then multiplied, we've then taken the tensor product of, and we get this richer space that's spanned by both of them.
Yep.
If that's true, I think that's a really nice intuition for what a tensor product is. Maybe, I don't know, maybe that's kind of
I'm not, for some reason, I'm not as maybe I don't understand the significance, possibly because I don't understand this categorical quantum mechanics stuff.
I'm mostly excited about this because I have had long arguments with various people about what the proper intuition for a tensor product should be. Right? There are all these different formal definitions, all these different kinds of intuitions you can give. But this one just seems so clean in comparison to all of them, right? It's just, you have a space that's defined by a type constructor, a multi-way constructor. You have a different space that's defined by a different multi-way constructor. The tensor product of those spaces is just the concatenation of those operators.
Okay, I agree that that's nice. Yeah, right. That is nice. That you can just say that a tensor product space is one that is constructed by the concatenation of its
concatenations of
constructors.
Right.
So that basically tells you that the tensor product, it's sort of I see.
So when we're constructing these fibration, and I mean, we should discuss, because, okay, when we're constructing these fibrations, what we're therefore doing is a partial trace operation, which means that our formulation of, again, if that's true, it means that our formulation of these branchial graphs as maps of entanglement is precisely correct, right? That what you do in order to, you have a collection of objects. Okay, the statement of entanglement is the statement that you can't trace out, so you can't do a partial trace on subsystems without losing some information that's then manifested as a density matrix.
Yep.
Right. And that's exactly what we're seeing, right? So when we fibrate this space, the fact that there exists these connections means we necessarily lose certain information, and so things become probabilistic.
Yeah, fair enough.
I think that's nice, right? So
that's very nice. Yes.
Categorical quantum mechanics kind of comes to our rescue and tells us that that actually our formulation of QM isn't as crazy as it might initially appear.
I don't think anybody's thinking particularly crazy. I mean,
it's nice to have independent verification at least.
Right.
But here what we have might even be more general than that, because in these examples you're just taking these nice graphs to make it illustrative. But if you start using hypergraphs, then this picture gets even richer, because now you're getting some in your branch space, instead of just getting vertices, you're getting the generalization, the hyper vertices. So it kind of makes this this picture of the tensor you have even more general than than the specific example.
Right.
And in a way, in the categorical quantum mechanics program, they only have planar diagrams. So they just keep everything in a kind of even though it's a tensor, they kind of organize it in a almost like in a planar way. Whereas here you kind of have all these hyper edges and hyper surfaces, so you have more ways to perform some kind of more general tensor type of operation.
I see. So something like this, you could not represent in a space like this, you could not represent in categorical quantum mechanics. Is that right?
So I suppose you could represent this, but if these diagrams themselves were generalized to hypergraphs rather than just graphs, okay, where you don't just have dyadic connections, but you have hyper edges, that would be harder to represent there.
Okay, so here's a question then. So even if we only consider strings or Turing machines or something, but we consider a thickened branchial graph, right? So these branchial graphs are thin in the sense that they only respect branchial ancestry up by up a single level. If we produced a thickened branchial graph respecting branchial ancestry up multiple levels, it would be natural to represent using hyperedges, because there will be multiple ancestors.
That's a good point, that we need branchial hypergraphs.
Implies branchial hypergraphs.
We need those. New construct. That's something to do.
And so Xerxes is saying, therefore, this is a more general tensor product construction.
But actually, my main point here is just the very observation that this thickened, instead of just making thickened graphs, we can actually make hypergraphs in the thickened case.
Yes, right, exactly. But that's interesting. I mean, it's not every day that you manage to construct something that's more general than category theory.
Well, okay, yeah, fair enough. Let's just go back for a second to the Rullial space business and infinity groupoids. Okay.
Yes. Okay.
Because one of the questions that we are get rid of that crazy error message. It's driving me crazy. That thing.
This thing. Sorry.
That's down. No. Okay. It was bothering me. It was.
I'm using the X kernel. That's the
crying
danger.
out for help. Anyway, so I mean, my question here is what is the claim about the mathematics that we choose to do, the axiom systems that we choose to have, versus all possible slices of the Rullial graph? So in other words, what we're saying is the univalence axiom, the things we choose to study in mathematics. Okay, first of all, in the whole treatment of everything we've said today, where have we used the univalence axiom?
Okay, so this is something that I think is worth clarifying. So this is new
topic, univalence axiom.
So if we have, so here's my basic claim, which you can feel free to disagree with, but I think this is my current idea. So suppose we have a multi-way system that's like this. So there are two separate branches.
Yep. So
far, we've been thinking about, there are two things we can do with this. We can fibrate it, which basically means we follow a particular path, or in a more general case, a particular collection of paths. Mm-hmm. Right? We pick a particular branch of history. Or we can foliate it, which means that we define equivalences between certain, between pairs of states or between sets of states, more generally.
Yes.
My basic point is those are actually the same thing. Foliations and fibrations are equivalent. For the following reason, right? So when we construct, if we take this thing and we construct, say, we do a canonical Knopf-Bendix completion on it, that's like we're foliating, because we're saying, okay, so hang on, let me. So this gives us the A goes to B, B goes to A rule. So that's just saying that we're defining a slice that connects these two surfaces.
Do that again with that added.
Yeah. Okay. Well, no, that's what I want to show, right? So I was intentionally leaving it suspenseful. It's going to get really, fair warning, it's going to get really complicated. But I'll do it for a simpler example in a second. It's going to give something really insane, right? But here's the point. So this completion is effectively defining a foliation, right? It's defining a flat foliation of this of the system. But let me do this with fewer steps so it's less obscure. Yeah, that'll do. If we now look at the states graph structure of this, let me do a layered graph plot. What this is effectively doing also is reducing this multi-way system so that it has only a single effective branch. Right? This had two effective branches, but this multi-way system now has one effective branch, because the addition of the completion rule means that even if you were on this branch, you can always hop to this branch.
Yep.
So up to the equivalence of this completion rule, there is only one branch.
Yep.
So essentially, you can think of rather than thinking of a fibration as just picking out a path, you can think of a fibration as being defining an appropriate set of equivalences so that all paths become that path, or that particular collection of paths.
Well, you're saying whenever there's a bifurcation, it's a branch pair, and that's the opportunity to make a completion across that branch pair.
Right. When we Okay. Oh, we can simulate vibration of a multi-way, say, of e.g. a Rulio multi-way system down to a particular multi-way system by just defining equivalences that collapse all branches that aren't the multi-way system we care about down to the multi-way system that we do care about, i.e. a foliation.
Right, so the claim is that there exists that a fibration following a particular path can be achieved by completions.
Right.
Or can be achieved by foliations, which is the original claim we were making earlier today, that models, that putting in models, which is foliation, is an alternative to defining different evolution rules.
Exactly. Okay.
So your claim is that univalence is some kind of statement about this fact. Is that your claim?
Basically, yes.
Do you think the univalence is deeply burnt into our models, or do you think univalence is an add-on?
This is going to bring us to a point of philosophical contention, at least between me and Max.
I know.
About yes. So is state equivalence important? Right. Univalence is really the statement that it is.
Max, by the way, claims that he's writing up something about his interpretation of quantum mechanics.
Cool.
So I look forward to seeing that. Yep. Okay, go on. So sorry, say that again. So
univalence is obviously just like all notions of extensionality is saying that equivalence actually matters.
What do you mean matters?
That you can define equivalences.
And that then they are crushed to identities.
State equivalence function in a multi-way system is a notion of extensionality.
Yes.
Is defining a notion of logical extensionality.
Right.
So the claim, the vibrations, this is a bit like propositions as types, the vibrations as foliations interpretation is claiming that when a pair of states are equivalent, then they can be treated as identical.
By virtue of a foliation.
Right, by virtue. Equivalent by virtue of a foliation, sure. Foliation / choice of completion rules. Whatever. This is precisely the statement of univalence.
Right, but they can be treated as equivalent, as identical, is the statement that the observer, that the mathematician, so to speak, what does can be treated as identical mean? That means that I still claim that the basic point here is that you can throw away the working. What matters is that these states are equivalent.
Yeah, that it doesn't matter which path you went down because the paths are the same. And the reason the paths are the same is because they lead to the same point.
So causal invariance, univalence, completability,
yeah,
are all basically the same thing.
Right.
And not only they're equivalent, they're also identical by virtue of this very idea. Okay, so the statement that we can do this in mathematics, what is the Okay, I was thinking about this. Like in a cellular, I mean, the question is, mathematics as done by humans, I believe, has crushed out all the working. So for example, in a cellular automaton, if you just say you can get from one state to another, that's a piece of mathematics you can do, but a lot of the richness of what's going on is how you get from one state to another. So
yeah,
the claim would be that what is special about human mathematics is all you care about. In other words, that Euclid cared only, it's like when Euclid wrote down his book, that human mathematics cares only about the results. Right, the intermediate computations, because they're not. So it's like the whole idea of human mathematics was, even though it's ironic actually, when I've talked to mathematicians over the many decades, they say the most important thing about mathematics and the thing that distinguishes it from computation is the idea of proof, and they're exactly wrong. Because in this interpretation, the whole idea of human mathematics is we mostly care about the end results. We don't care about the process. The process is what computation cares about.
Proofs are an excuse to care only about the theorem.
What do you mean by that?
That the reason why mathematicians care about giving proofs of theorems is so that they don't need to. So that once the proof has been established, you can just use the theorem without having to repeat the logic of the proof, right?
Yes.
To care only about the theorem without repeating the logic of the proof in subsequent.
Right. So that is a statement of, I mean, in sort of in the universe in physics, it is, the journey is the story, so to speak, for our existence. Yet in mathematics, it's the destination, which is what's important. Right? In physics, it's all about, I mean, in our experience, it's all about the journey, so to speak. Yes, right. It's only whereas in mathematics, it's only about the destination.
Right.
So SWSH Nick here asks, can you use each completion rule as a coordinate within the foliation?
Sort of, right? I mean, it's defining a coordinate axis, I would say.
I think that's right. Yeah, I think that's right. I think is it defining? It's defining a way of crushing things. It's defining an axis in the sense that you're defining a set of equivalences.
Right. Everything that's completed by this rule is on the lies on the same axis in this.
It's collinear in some sense.
Right. Okay. Yeah. No, that's nice. So I like that. So critical pair lemmas are defining collinearity of propositions, or of terms, I should say. Sorry.
Right. Nick quotes also here from Vladimir Arnold. Mathematics is part of physics, according to Arnold. Physics is experimental science, part of natural science. Mathematics is the part of physics where experiments are cheap. Mathematics is part of physics. I'm afraid my vision of Arnold is forever tainted by the fact that I first met him in maybe 1991. I was visiting Russia, and I had somehow gotten sick, and I had a temperature of like 104 degrees Fahrenheit. And I was desperately trying to find some non-polluted water to drink. And that was anyway, never mind.
Sounds dramatic.
Well, yes, right. And that was, the question was, where could one find that? Anyway,
Well, I mean, I guess it's true in a sense, right? So I probably don't have the philosophical chops to carry out this argument, but if you view this generalized view of physics as being just foliations of the Rullier multi-way system,
yep,
physics is about the whole, foliation of the whole thing. Mathematics constrains itself only to foliations of patches that have reducibility. So in that sense, mathematics is part of physics.
Well, maybe. I'm beginning to think that the real point here I mean, I have long thought that mathematics was sort of the reducible pieces of the computational universe, so to speak.
Right.
I have to say that this is making me slightly change my mind in terms of the concept. I don't know. We probably are running out of steam here. I think this is we figured out. We still need to hear about the full story of the infinity groupoid, and
yes,
your full story of why you think things get inherited from the Rullier from the structure of Rullier space.
Right.
I mean, because that's one of the claims, is that there are features of Rullier space that are inherited to every sub-fibration of Rullier space, so to speak.
Right, exactly. That's the section I'm planning to write next, hopefully.
Okay. All right. Well, listen, by the way, before we wrap this up, please make sure you save these notebooks in the working thing.
Yep. I will put those in working notes. Even though I suspect this one will be absurdly huge because of these ridiculous group structures that we've... I suspect that's big.
Yeah, don't worry about it. It's okay. Just put it in there. It'll get processed properly. I have complete faith. You can call it Metamathematics. The previous one was supposed to be Metamathematics 5. I had another one which was Metamathematics 6, so there's Metamathematics 7.
Oh dear, okay. We should start adopting church numerals or something.
No, I think we should go transfinite.
Ah, yeah, yeah, that might be better.
Are you going to...
Sorry, that's just, you've made me think about something silly now.
What?
So you know about Turing's PhD thesis?
Yes. The ordinals, systems of logic based on ordinals.
Yes. So what would a model based on a transfinite ordinal look like?
You mean...
If interpreted as a foliation, what if we were to take a model that was defined by a transfinite ordinal in Turing's hierarchy as opposed to one that was defined by a finite ordinal? What would the difference be?
Well, isn't that your thing where you can go in? I mean, it's a tachyon thing, isn't it?
I guess, but there are. How do you see the hierarchy of transfinite ordinals? If there's only one speed of proof.
But there isn't. It's the same issue as you can have sort of the Rullier graph. There are an infinite hierarchy of Rullier graphs defined by hypercomputational Rullier graphs.
Well, that's interesting. I think that's kind of interesting if that's true. So what we're basically saying, right, is models based on transfinite ordinals define foliations in higher order.
Rullier graphs.
Right. So
yeah, in which an infinite chain in an ordinary multi-way system has well, maybe, but I think the whole point is that these higher Rullier graphs are ones in which an infinite chain in this Rullier graph has been compressed to a single, has been compressed to something finite, right?
Right, exactly.
I mean, that relates to these infinitary combinators that you have been avoiding, that I still think are worth studying.
I think they're worth studying. I'm just, I can't, I'm not yet motivated to.
Fair enough. I mean, I just think that they're going to look. I honestly, I think that they are outside of But your statement, your claim about the Grothendieck hypothesis, about the relationship between Rullial graphs and the notion of a geometrical space, your claim is that that feature is then down inherited to all of the fibrations of the Rullial graph, right?
Right. Because when if you fibrate a topological space, each fiber is itself a topological space.
And what is the significance? What is the everyday significance of the fact that the Rullial graph is a topological space?
Well, I think it explains why physics takes place in spaces, and why we have notions like continuous space-time and projective Hilbert space and things. Right? There's geometrical topological structure that's being inherited from the Rullial topos.
And you think that exists because you can define these homotopies, because in Rullial space there are naturally all these tons of homotopies that have to exist.
Right, exactly.
And that those homotopies sort of knit things together enough. So the basic claim is the homotopies inevitably exist.
Right, the homotopies, in Rullial space endow it with a spatial structure,
right,
which is then inherited by all lower order objects, including, e.g., Hilbert space.
And our famous space-time in which we live.
Physical space, etc. Right. So it kind of, if true, answers the question of why do we perceive space-time and not just a causal network?
No, why is it possible to perceive a space-time? Why is it that there's a space-time that can be constructed? I'm not certain that that's I mean, these homotopies are the result of correspondences of paths deforming into paths deforming, these higher order paths deforming into each other, right?
Right.
And why do you need to go to the limit of Rullial space rather than seeing those homotopies in some lower space?
So it's because, a few reasons. So one is it's only in Rullial space that you get guaranteed invertibility of morphisms.
Okay, that's a fair point. Yes.
And then also, and that corresponds. Okay, so
in other words, it's only in Rullial space you can get a groupoid as opposed to some weak category thing.
Exactly. And so the point is that in ordinary, in the ordinary Grothendieckian construction, that infinity groupoid has this nice property that it has this weak homotopy equivalence property, that if you have two paths that are homotopy equivalent, basically homotopy equivalence in the infinity groupoid implies homotopy equivalence on all of the lower order structures. So it's that homotopy equivalence is inherited by all the lower order structures, and that's a property that's unique to the infinity groupoid.
That everything below it inherits those homotopy?
Yeah, right. So if you have one topological space and then you define its higher order sort of homotopy space, then it's not necessarily the case that equivalence of homotopy equivalence in the higher order space implies homotopy equivalence in the lower order space. That's not generally how it works, but it does in the case of this infinite hierarchy for the infinity groupoid. That's why in the ordinary
growth to achieve that, but the infinity groupoid in a sense is an aggregator of the whole tower of lower spaces, basically.
Right.
Lower objects, whatever they are.
Right.
What is the right definition of a space? What do we mean by it? What is a space?
Crikey. Xerxes?
Because informally, particularly in modern times, I mean, I use the term space to refer to almost anything where there's lots of things in it.
Right. I mean, the definition that I know is that it's a set, it's set endowed with some additional structure. But that's a very set theoretic definition.
Yeah, but what additional structure do you need?
Right. So
nearness, paths, I don't know. Maybe if you have no idea what's near what, can it still be a space? I think it can be.
Yeah. Yeah.
I think it's become a common term for just big, big collections of things. So, for example, can we call it proposition space? Is that a reasonable thing to do, even though we know nothing about its structure?
I'd say so.
You think so?
Yeah.
I do too, but I mean, I don't know. Mathematicians, can be very persnickety about these things.
Sorry, please.
In our case, we try to for many physical purposes, we try to think of spaces as those things where some sort of geometry lives. Of course, for mathematicians, geometry is too special. Space can be something that doesn't have geometry, just has topology. But if you just ask like what kind, why does geometry come with these type of infinity structures? The way what you can kind of loosely build this argument is by saying that once you have homotopies and you have paths and multiple levels of homotopies, you can start asking how between these paths, you can then start using these homotopies, you can start making the link to objects like cohomologies, which naturally link to homotopies. And from cohomologies, you have differential forms. From differential forms, you can dualize that and get to the notion of tangent vectors and vector bundles, and then you get the rest of more familiar geometry. So in some sense, from this tower of infinite homotopies, you can build almost all of the rest of geometry. So it's from a physics point of view, that's a very fundamental notion of thinking of space. From a purely mathematical point of view, you don't need geometry; it's too strong already. But even there, the homotopies at least give you a good way to start thinking of topology, and there again you get the notion of space. So in that sense, though I've not defined space, I'm just trying to say that from homotopies you can construct many of the interesting examples of where you define spaces either in mathematics or physics.
Well, this gives us a potentially very circular definition of space, right? So we could have a circular definition of space. Any feature that is inherited from weak homotopy equivalence in the infinity groupoid.
Yes, great.
But this does bring up the question of so geometry is too special. I agree from a mathematical standpoint. Is topology too special? I mean, can you have a space that is non-topological?
Right. What do you mean? In topology, don't you need to have? I mean, like in the case of our hypergraphs, for example, I don't think they define a topology in any interesting way. You have to have you have to know about faces and things like that, don't you? I mean,
no, I don't think so. You could easily define. I mean, they
define
kind
of topology.
They define I mean, all graphs define a topology.
Yeah, fine. But in this sense, you can define a topology for anything, probably.
I mean, you can define a trivial topology for anything. You have the discrete and the indiscrete. So in a sense, the trivial can always be found. What's interesting is when there's a non-trivial topology. So in that sense, you could almost always define a topology.
Okay, but the basic thing...
Can you have a space with only a trivial topology?
The basic claim in all of this is, okay, the fact that we can make sense of the physical world and we're not thrown into irreducibility is a consequence of our, essentially our use of this notion, what's equivalent to the invariance axiom, causal invariance, et cetera, et cetera, et cetera. That allows us to both not be, it seems to allow us to do two things. It seems to allow us to both have an objective reality, because it doesn't matter what path we follow, so to speak. Objective reality is the same thing as this idea in math that it doesn't matter how you got there. That's right. It's the same basic statement.
Mm-hmm. A kind of causal invariance of mathematics.
Yes. Yes, and that's the statement that it doesn't matter which proof you used.
There you go, yeah.
Right. Right. All right, well, so interesting. So what we basically, What we're basically saying is we are quantifying certain aspects of metamathematics which have never really been quantifiable before in this way of thinking about I mean, it's a very, multi-way systems and proof systems. Another one is the hypergraph, branchial hypergraphs is another one.
Yeah, branchial. So hypergraphs investigate hypergraphs as a
thickening.
Yeah, as a way of representing thickened branchial graphs. But that's not really that's more general than the metamathematics stuff. That's a thing that's worth investigating.
Right. Well, and then the next thing is between multi-way systems and proof objects. The next thing is the empirical study of proof objects.
Right. So empirical study of proof objects using finite equational proof, attempting to determine the analog of the Einstein field equations, i.e. the relationship between critical pair lemma density and causal edge density. Brackets in particular directions.
Thinking of obstructions in proof space.
Say that again?
Thinking of obstructions in proof space.
Yeah.
We still have to think about that.
What are topological obstructions in proof space, or for that matter, in
quantum mechanics,
Rullial, branchial space, etc.?
What the heck is that going to be? Even in branchial space, what is that?
It might well be that in the end we don't need to really worry about these obstructions themselves, because we are thinking of them a lot like particles. Instead, later on, when we understand better how these connections in the fibers are, and we have the notion of how to define fields as one forms or two forms or whatever, when we have fields, some kind of quantization of those fields would manifest as these obstructions or particles. So by thinking of fields, we might solve this problem kind of more elegantly.
So I think I know, or at least I think I have a reasonable conjecture as to what the answer is for Rullial space, at least when interpreted in a particular way. So, okay, so conjecture about topological obstructions. So interpret topology of Rullial space as computability theory. Interpret induced geometry as computational complexity theory. So then reducibility of one complexity class,
I see,
to another is a is a diffeomorphism of some kind.
Yeah.
Probably quasi-conformal. Implies topological obstructions are the complete problems, e.g.
Right. NP completeness.
Which prevent such a diffeomorphism from being constructed, which is the thing I'm trying to, do I have it open?
What?
Oh, never mind, no.
So this is your NP completeness thing.
Yeah, right.
How is it going?
It's good. I've been distracted by writing up something else, by writing up this metamathematics thing. But hopefully, I can have the NP completeness thing working soon. But yeah, basically, so in the context of complexity theory, I can interpret it as I have an interpretation of the topological obstructions as these complete problems. So then the question is, what's the correspondence between complexity theory and model theory? What's the analog? Are there sort of we need to know what the analog of NP complete problems are in model theory.
Right. Well, we even need to know the quantitation of model theory isn't really there. I mean, there aren't really model classes in the same sense that there are computational complexity classes, are there? Or are there? I don't know.
I haven't heard of them, but you should find out.
It's just a speculation. Is there a way to think about this thing by trying to maybe use some instance of the Curry-Howard correspondence in which we think of the proofs as the syntactic side and the models as the programs, and if you think about it that way, then these paths that we talk about are in fact the programs, and when something is a kind of hyper, when, for the example that you gave a few comments above with this transfinite thing or something like this, then if a program is outside of being constructible or not something that you cannot possibly construct, then it's sort of hypercomputation. And if you think about it that way, then this question of what type of classification of models we want to give becomes something about a classification of the type of programs, those that are computable, non-hypercomputable, etc.
And which have certain complexity classes.
Yeah, exactly.
Therefore, we can discuss complexity classes of
I see.
models.
So then also the kind of question that we are talking a little while before about these foliations, we are talking the speed of proof. So in that sense, if we interpret the model space as program space, then the speed of proof has basically two elements. One is how long does it take on a particular path, and whether we have enumerated all the possible paths. So that's really like doing a path integral, with the choice of the measure is like a choice of foliations. And this path integral in proof space is really a, sorry, not proof space, in program space, is then sort of telling you the speed of proofs, because now it is taking into account all the possible paths or all the possible programs along with the length of each. And that gives you some notion, that might give some notion of how much are your limits in the speed that you can transfer. I'm not sure if speed is the right word, but I'm thinking about it in that way. So maybe the Curry-Howard correspondence is kind of helping us in a way to make this link between proofs and models more clear. Though in the language of categories, they would probably not talk about it like this as programs and proofs. They would think about it more as syntax and semantics. But for us, models which are semantics can be realized in one way by thinking about them as programs, and or hyper programs or whatever, what cannot be constructed as well.
So bottom line, we can computational complexify model theory.
I think we should ask a model theorist. Maybe I'll ask my friend, the model theorist, that question of whether she knows whether that already exists. I mean,
I'm sure something like it does. I mean, it seems like the kind of thing model theorists would investigate.
Yes. The only question is whether it's like these, it's these communication issues of these incoherent views of the world. Is, can one communicate with a model theorist?
Right.
Right. There was one question from Quinn here. What about a proof using the axiom of choice versus a proof of the same theorem not using it? Yeah, that has to do with our whole story of models. And
right.
That was,
so I mean, we have an example, right? So if we have, so here's, so if you consider proving, say, the proposition that this node implies this node, then a proof using the axiom of choice would say follow this yellow path, whereas a proof not using the axiom of choice would follow some internal path. Right.
Right. All right, we better wrap up here. Making good progress, guys.
This is good, yeah.
It's yeah, we're going to get, if we can check off, physics check, mathematics check, we're in good shape. Then we just got to do our we got to figure out the relationship between quantum interference and distributed blockchains. That's coming soon. I think Max said he was working on that. All right, good stuff. Okay, we better wrap up here.
Cool.
Thanks to folks here. Thanks to folks on the live stream. And we will continue. And Jonathan, I would like to, if you're not about to, oh boy, I'm about nearly an hour late for another meeting, which I really have to go to. But I would like to ask you some things about some completely unrelated topics. And terrific. Okay, thanks, Xerxes. Thanks, everybody. Thanks to the folks who've been running this live stream on a Saturday. Off we go. See